start the stream. Hello all, whoever is present. Welcome to my stream. Let me tell something about myself. I am Advait. I am a fourth year computer science student from India. So I am interested in computer security, some low level stuff like binary exploitation, operating systems, networks, vulnerability research, etc. So today is my first stream. I'll be discussing a really interesting exploit technique called return oriented programming. So it's an experimental stream. I mean, it's really new to me. I've never done something like this before. So before starting the paper discussion, I just want to tell why I wanted to start the stream. I want to put it right out. So I have a couple of limitations myself. Basically, I think that I don't speak so fluently. I feel I can do better. So we are all in the lockdown period, so there's no chance of me going out there and discussing and explaining stuff to other people on a stage, for example. So I thought, okay, streaming is the best option to do that, and it's also new. That is one thing, and second, I think the more important reason is in the seventh semester, in the previous semester, before our college closed abruptly, we had this course called high performance computing. So there the course was really unique, and the concept was really different. Basically every week we had to read a paper and discuss it. Basically the class was divided into teams, and each team would come every week and then read a paper, explain it to the class in detail. I mean, that was the idea. So I really liked that idea. I wanted to continue it. So I don't think I'll be able to do one paper a week. That is a bit hard. But I'll make sure I discuss some really interesting papers. So with that being said, I think we are ready to go. We'll just wait for 5 more minutes. Wait if someone turns up, and then let's get started. Yeah. Okay, so let's get started. Okay, so let's get started. So again, I'll just introduce myself. I am Advait. I'm a fourth year computer science student from India. I'm a computer security enthusiast. So I really like low level stuff, binary exploitation, reverse engineering, operating systems, networks, computer networks, a bit of crypto, and so. In today's stream, we will be discussing and exploring a really interesting exploit technique. It's called return-oriented programming. So why this paper? Why this paper? So the first paper came out in 2007, and it made a lot of noise in the security community because it proved to be a really effective exploit technique against certain types of vulnerabilities. So one more thing is in 2017, this paper won the Test of Time award. That is, after 10 years, the paper came out. It won the ACM Test of Time award. So not many papers get this. So I found this really interesting. It is actually interesting. So that's about the paper and about the methodology, the way how do we go about the paper in this theme. So I'm planning to do something like this. First, we'll read through the paper word by word, literally word by word. Say we introduce return-oriented programming, and then wherever some word or some phrase needs more explanation, I'll stop there and let's take a deep dive into it. So that is the idea. It's like DFS. So you read, and then you don't understand what is this injecting any code. So we'll stop there. We'll take a deep dive into injecting any code, and then come back and then proceed. So that is how it's going to be. I think without further ado, we'll get started. Okay. So before starting the paper, let me just. You can download the paper here. Yeah, so this is the link. I mean, if you just type in return-oriented programming, the first or second link, yeah, this is the third link here in DuckDuckGo. So you'll get the paper right away. Yeah, so we'll be referring to that paper. This is the one. It's a 42-page paper, just for reference. It's a pretty long paper. A lot of concepts are involved in it. A lot of history about attacks and defenses are involved. How people came up with exploits, attacks for certain class of vulnerabilities, and then the defensive community came in and put in defensive mechanism, and then to break that defensive mechanism, offensive community came up with one more type of attack. So it will be a series of attack and defense techniques. So this is an attack technique, really effective one, I can say. Okay, so let's get started without any delay. Return-oriented programming, systems, languages, and applications. We introduce return-oriented programming, a technique by which an attacker can induce arbitrary behavior in a program whose control he has diverted without injecting any code. So this first line has a lot of weight in it. It has a lot of meaning. It actually tells in short what return-oriented programming is about. So we introduce return-oriented programming. That's the new technique, a technique by which an attacker can induce arbitrary behavior in a program whose control flow he has diverted without injecting any code. So first we'll understand what you know who an attacker is. So an attacker is any person who wants to take control of a machine, can induce arbitrary behavior in a program. So let's talk about this arbitrary behavior in a bit more detail so that we are clear on that. Okay. So let's write a simple program to understand this. Okay, so you'll be dealing with a lot of we'll be writing code in mostly C and Python, Python for exploits and all that. Okay, we'll also be writing a bit of assembly too, so you will have to get used to it. Okay, so this is a simple program which will call a function outside of which will call a function. That's it. Nothing much. So we'll define the function here. So we'll define a buffer of 100 bytes, and then we will get the input from the buffer, input from the user, and then print it back. That's it, nothing more. It's a fairly simple application. That's it. So basically we call the function, and then in the function we allocate some bytes as a buffer, and then we take user input and then print it back. Simple. So we'll go ahead and compile this. So one more thing I want to tell about this paper is that this paper deals with 32-bit Intel architecture. So all the attacks and all the techniques it describes are with reference to the 32-bit, the x86 architecture. So though I am running a 64-bit system, I'll be explaining these with 32-bit executables. So let's compile it. So M32 on a 64-bit system with this M32 flag, you can generate a 32-bit executable. So yeah, so because we are dealing, the paper references only 32-bit architecture, so we'll just go ahead with 32-bit. We'll just put in the debugging symbol, then let's compile. Okay, so we got two warnings here. Warning: implicit declaration of function getS. Did you mean fgetS? Okay, so I think we missed a header file, so that is okay. Second, it's a linker time warning. So warning: the getS function is dangerous and should not be used. Okay, so you will come to know in a while why this is dangerous and should not be used. That's okay, we'll just ignore it for now. So we'll run the program. It's very simple. It is expecting some user input, we enter, and then it will give back. So we'll just put two markers here which will mark the entry and end of the function. Okay, wait, before we do that, I hope you are able to. Okay. After func, so these are just markers which will tell we are entering the function, we are about to enter the function, and we are done with the function. So this will help. So we'll compile it again. Same errors. Code 1. Okay. Before func, so it's expecting an input. We enter something, we get back. So you have seen echo functions, right? I mean, cat is in itself an echo program if it's working on the STDN. So look at this. So our program is something similar, just that it doesn't run in an infinite loop. It just runs for once. Yeah. So that is the program. So here the idea was to talk about arbitrary behavior. So to talk about arbitrary behavior, we need to define what the actual behavior is. What is the intended behavior of this program? So let us define the intended behavior of this program. As programmers, we write a program to solve a problem with a certain intention. So even this program has a fairly simple intention, simple use. So it's an echo program. That's it. So it should take user input and give it back, print it back. That's it, nothing more. So coming to the intention, coming to the behavior of it, this is how it should behave. So enter main, we need to enter main first, and then the printf, the first printf should get executed. And then call to the function. Okay, here allocate buffer. Although this is invisible to the user wouldn't feel the allocation of a buffer. So next, so you take user input, print it back, go back to main, and we are back. We are back to main here. Now second printf. Later you return and then exit. So this in short is the intended behavior. Nothing apart from this should happen. So this is the intended behavior. But here in the paper we read that by which an attacker can induce arbitrary behavior. Induce is basically generate arbitrary behavior. What is arbitrary behavior? The attacker may be able to do anything he wants. That is the idea. So here he can't do anything he wants. He can just input something and get the output back. He can't do anything he wants. But the paper is telling that this technique would allow you to induce arbitrary behavior in a program whose control flow he has diverted without injecting any code. So that was arbitrary behavior, basically any deviation from normal behavior of a program in a program whose control flow he has diverted. Okay, so even this is something important. The behavior is more or less the control flow. Control flow is also this main, printf, func. The four things happen and then back to printf and back to main. So the control flow is very simple. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, so this is the control flow. But given that the control flow has been diverted, the attacker can induce arbitrary behavior. That is what the paper is telling. Somehow this order should be disturbed. So this order should be deviated, it should be disturbed. Say for example, you enter function and then never come out of it. You simply crash the system by doing something or something like that. So basically you deviate from the normal control flow. With after doing that, ROP can be used to induce arbitrary behavior without injecting any code. Okay, so here the author is referring to a really powerful and a traditional way to exploit certain class of vulnerabilities. We'll come to that. They're referring to an attack technique basically. Code injection is an attack technique. We'll come to that in a while. Okay, let's continue. A return-oriented program chains together short instruction sequences already present in a program's address space, each which ends in a return instruction. Okay, so they're telling that they're talking about return-oriented programs here. So it chains together short instruction sequences already present in a program's address space, each of which ends in a return instruction. Okay, so let's just see what they mean by this. Okay, so we'll take, so if they're talking about return instruction, then we need to go to the assembly level. We can't analyze the code at the C level still. So let us take the assembly, let us disassemble code 1 and put it in one more file. So we have the disassembly ready, basically the assembly equivalent of the C program. So this is it. So here it has a lot of stuff, don't worry about it. So we come to the main function here. So this is the assembly equivalent of the main function we wrote, and so this is the assembly equivalent of the func function we wrote, the second function. So here they're talking about short instruction sequences already present in program's address space, each of which ends in a return instruction. So you can see everywhere here that there are certain sequences with which end with RET. So here look at this. So this is a short instruction sequence. Leave RET. So okay, we'll open up one more window. So leave comma RET is one such short instruction sequence, basically a contiguous sequence of instructions which end with RET instruction. That is what they mean. Add ESP comma 0x10 leave comma RET. This is also one more sequence. And taking some other example. Okay, so here you can see there's a move. There is a move EDX comma D word ESP RET. So this is also one more sequence. So any sequence which is ending with RET, that is what they mean. Why is this important? We'll come to that in a while. Okay, let's continue. Return-oriented programming defeats the W XOR X protections recently deployed by Microsoft, Intel, and AMD. In this context, it can be seen as a generalization of traditional return into Libc attacks. But the threat is more general. Return-oriented programming is readily exploitable on multiple architectures and systems and bypasses an entire category of security measures. Those that seek to prevent malicious computation by preventing the execution of malicious code. Okay, so this paragraph also, because this is an abstract, it's quite heavy, so we don't have to go into detail in the abstract because the whole paper is about going into the technique in detail. So let us just skim through the abstract. I'll give you an overview of every word, what is happening. Later, while we read the paper, we'll be able to understand each and every word which has been used in the abstract. So don't worry about it. So ROP defeats the W XOR X protections recently deployed by Microsoft, Intel, and AMD. Okay, so W XOR X is a security technique. It's a defensive mechanism deployed by major operating systems and even processors. So processor manufacturers basically found this security mechanism really effective, and they changed their architecture to implement this security protection, the W XOR X. So it's spelled this way, W XOR X. So it stands for write, XOR, execute. So it stands for write, XOR, execute, right? So we'll see what that actually means in a while. So you can think of it as a really good security protection. It's a defense mechanism. In this context, it can be seen as a generalization of traditional return into Libc attacks. So return into Libc is a very it was I think invented in 1999, a long time ago. So this is a very effective exploit technique. This was a very effective exploit technique to break certain security mechanisms like W XOR X. So what they're telling is ROP can be seen as a generalization of this technique. So unless we understand what return into Libc is, we can't see how ROP is a generalization of return into Libc. So as we read through the paper, we will look at examples. I have a few demo programs to show what return into Libc is, what exactly can it do, how powerful it is. So okay, but the threat is more general. Return oriented programming is readily exploitable on multiple architectures and systems and bypasses an entire category of security measures. Those that seek to prevent malicious computation by preventing the execution of malicious code. Okay, so this line is very, very, it tells a lot about what the security community, what the security industry has done so far to prevent malicious computation, to prevent attacks. So we have a lot to talk about this particular statement. Okay. We'll just go back to the streams main. Okay, everything is going good. Right. Okay, so how do we prevent? Okay, so I have an example. Let's take an example. Let's take an example here. Consider we have a, we'll take a circle. No, just take this. Consider we have a network. So this is a network. So this is a network, and then obviously it has a gateway. So let's put in the gateway here. Gateway router, and here inside we have a server. Some server, you can think about it as a web server if you want. So some server running. So this is, we have a setup something like this. So we have a gateway router for a network, and inside the network there is a server, and a certain number of people have access to this server. So with this given scenario, how do we protect the server from attackers? So that is the question. So let us try to think about it. Just close this. Close. Okay, now it's visible, right? How do we protect the server from external entities, external attackers? So here comes the hierarchy of security mechanisms which are put in place to make sure the server doesn't get attacked. So at the gateway, so there are, you might have heard of firewalls. Basically, they go through each and every packet which flows in and out of the network and make sure nothing malicious is happening. Make sure there are certain rules are in place, and every packet follows that rules. So one more technique is having access control lists. So consider this to be your office network, and you have access to one of your development servers. So having an access control list is, so you have access to this server, 10 other employees have access to this server. Basically there is a whitelist and a blacklist. So in the whitelist, it's basically a list of all the people who have access to this server. A blacklist is basically everyone else who don't have access. So this will help in making sure who has and who doesn't have access to this server. This is also when it's coupled with other security mechanisms, it's pretty effective. And then we have something called intrusion detection systems. Right. So you might have heard of IDS or IPS, intrusion detection or prevention systems. So they basically, certain rules are written in them, and then they basically detect if someone is trying to attack anything inside the network. So, and there are also systems which try to prevent them. Once you detect it, you either alert the sysadmin, or there are preventive mechanisms in the IPS itself, which can prevent it. So these are at the gateway. Suppose the attacker goes through the gateway, he will bypass the gateway, and then he is now at the server. What do we do now? Okay, give me a moment. There's some external noise here. Okay, I am really sorry about that. I can't, it's sort of out of my control. So farmers are coming in street by street and they're selling tomatoes and vegetables because they can't go to markets. So we'll just have to adjust here. Okay, so coming back, suppose an attacker has bypassed the three the three security mechanisms here. Now he's at the server, he's trying to hit the server, he has some contact with the server. How do we make sure his exploit doesn't work? That is the idea. Now that he has come till the server, how do we make sure his exploit doesn't work? That is when this comes in. Here we can have an antivirus software. We can have an antivirus software. What does an antivirus software do? If someone tries to run a new executable, the antivirus probably won't let it run directly. What the antivirus will do is, it will run the executable on its sandbox, make sure it's safe, it's not a virus or it's not malicious, and then go ahead and it will let the user run it on the actual machine. So that those that seek to prevent malicious computation, preventing the execution of malicious code. So here, if the executable is malicious, then the antivirus is preventing the execution of malicious code. If virus doesn't get executed, then there's nothing to worry about. It will obviously prevent malicious computation. That is the idea. So there is a hard implication here. Prevent execution of malicious code implies preventing malicious behavior. So this is the implication, and this is how most of the security mechanisms are designed. Even in firewall or the IDS IPS, if some malicious behavior is observed, the IDS will block the IP which is trying to attack. So it is basically preventing the execution of malicious code. So this is the implication around which many security software have been written on. So that so what ROP is trying to do is it is able to break this implication apart. So with ROP, this implication is broken. Okay, I hope you can understand this. Basically breaking the implication, it's a slash sign here across the implied sign. So okay, basically preventing so what they mean is, even without execution of malicious code, you can induce malicious behavior. That is what they're trying to tell. How that is done, that's the body crux of the paper. So this was very important. Okay, so do you have any feedback or suggestions so far? Anything which... Okay, great. I don't think anyone is watching, so it's me. Okay, to demonstrate the wide applicability of return-oriented programming, we construct a Turing-complete set of building blocks called gadgets using the standard C library from each of two very different architectures, Linux x86 and Solaris Spark. So they consider two very different architectures. They are really different. x86 is I think x86 is a CISC computer, Spark is a RISC computer, and there are a lot of differences in the way it handles memory and the size of the instructions, etc. So we'll come to that. So what they're telling is, we construct a Turing complete set of instructions. So they are able to construct set of building blocks which will allow us to compute anything. Okay, I don't clearly understand what Turing complete is in detail, but all I can say is one can execute anything okay, I'm blank here. Anything computable. We'll come back to this point later. Okay, to demonstrate the power of return-oriented programming, we present a high-level general-purpose language for describing return-oriented exploits and a compiler that translates it to the gadgets. So here, apart from the exploit, they're trying to automate the exploit here. They present a high-level general-purpose language for describing return-oriented exploits. So probably writing ROP exploits is hard. So what they're trying to do is they're trying to build a tool which will a compiler which will help in writing the ROP exploits. So that was the abstract of the paper. So it's a new security technique, it's a new exploit technique which helps in getting control of the system without injecting any code, and it also tries to breaks mechanisms which are deployed by a mechanism deployed by Microsoft, Intel and AMD, and it breaks this really hard implication which the security software are written on, the antivirus software or the IDS, etc. And they have demonstrated the attack on two different type of architectures, Linux x86 and Solaris Spark. So that is what they mean. So with that was the abstract. So let us, okay, so before going to the introduction, I just want to give a small overview on what we are dealing with, how the security as a field has been branched, and where does ROP come under that branch. So we'll just remove all this. Okay. Okay, let it be there, it's okay. So we start with security. And from there it can be divided into two parts. Offensive sec and then defensive sec. So what offensive security means is basically you're trying to find vulnerabilities, you're trying to attack the system, and that way you make sure you close up all the bugs, you find out new bugs, new vulnerabilities. That comes under offensive. See, the word offensive means that. So defensive is about the other way. So once the vulnerabilities have been found, how do you defend a system from attacks? So this is, we'll just write it here. Okay, it implies that. So this is about defending systems, this is about attacking the systems and finding new things, finding new bugs, new vulnerabilities, and finding a new exploit technique. So under defensive sec we have, say, security software like this. So firewalls come under this, IDS, IPS, then antivirus software. So but in the offensive sec, it's about finding vulnerabilities. So it can be divided, say, I don't think it can be divided, but let us simply put two branches here. So one is exploitation, other is vulnerability research. So here vulnerability research is basically finding new vulnerabilities finding new methods to find bugs, to find vulnerabilities. It's about finding vulnerabilities and methods to find. So exploitation is about once you find a vulnerability, how do you exploit it? So you know the vulnerability and now you want to find various ways to exploit it and get control of the system. So that is about exploitation. So here comes various techniques. So in vulnerabilities we have, say, stack. We have various vulnerabilities. There are n number of vulnerabilities. A bunch of popular, infamous vulnerabilities are stack overflow and say format string, SQL injection, etc. Exploitation is about exploiting these vulnerabilities. In SOF, to exploit SOF, there are there are a couple of things. Say the author spoke something about return into Libc. So that is actually a very interesting attack against this. And the author also spoke about, just put a couple of lines here. Author also spoke about injecting code. That is also one exploitation technique. And today in this stream we are discussing ROP. This is also one exploit technique. So in computer security, this is where ROP stands. So it's part of offensive sec and it's an exploitation technique. So I just wanted you to be clear on this. Okay, that is what we are discussing, a new exploitation technique. With that, I think we can go to the introduction. Right. The conundrum of malicious code is one that has vexed the security community. Since we cannot accurately predict whether a particular execution will be benign or not, most work over the past 2 decades has instead focused on preventing the introduction and execution of malicious code, of new malicious code. Roughly speaking, most of this activity falls into 2 categories: efforts that attempt to guarantee the integrity of control flow in the existing programs, such as there are a few examples: type-safe languages, stack cookies, XFI, and efforts that attempt to isolate bad code that has been introduced into the system: WXORX, memory tainting, virus scanners, and most of trusted computing. So this paragraph tells a bit about what has been done, how what is the problem faced by the security industry. So the conundrum is basically a very critical problem, is one that has long troubled the security community. So here they talk about predicting if a particular execution is benign or not. So let us talk a bit about this. So benign is basically non-harmful. You might have heard of benign and malignant. Malignant is harmful to the body. Benign is not harmful. So here we are talking about execution which can be non-harmful or harmful to the system. So they're telling that predicting it is really hard. We cannot predict whether a particular... Why is this hard? So that is something let us try to understand that. So for an operating system, it actually doesn't care what is being executed. So what I mean by that is, the operating system gives a bunch of system calls, a bunch of interrupt mechanisms for programs. So, and I don't know if there is any, there are a couple of other APIs which are offered. So with these 3, any program can interact with the operating system, can request for resources, can stop the operating system and request it to do something. So using these 3 APIs. So how do I differentiate between a normal program executing these APIs given by the OS and a virus? So we have a normal program and we have a virus. So even a normal program uses system calls to, system calls are literally the heart of the program, I can say, because you read, write using system calls, the file opening, closing is using system calls, everything is using system calls, the networking, from a program point of view, everything happens through system calls. So when a normal benign program is using the system calls, it's actually benign, nothing will happen. When the virus is using the same system calls, it's actually malicious. But how will the operating system know? So that is the question. So that is, the operating system finds it really hard to find out if a virus is actually executing it or not. That is the problem. So the OS doesn't really know if a malicious program is executing the system call or not. So that's why we can't predict a particular execution is benign or not. So okay, so most work over the past 2 decades has instead focused on preventing introduction and execution of new malicious code. See, because it is hard to predict, so there are 2 approaches here. One at runtime approach. So at runtime approach, it means once the virus is running, the OS will detect that it's a virus running, it's not a benign program, we need to kill it right away. So that's the runtime approach. You need to predict it clearly. Second is preventing running of virus. So one is the runtime approach. Second is you just don't allow to run the virus on the OS. Leave predicting it later. So if you don't run the virus, you obviously don't have the fear of malicious behavior. So most of the work so far has gone into this second category because it is hard. Because this is hard. Work has gone into the second category, most of the work. So we can see antivirus software actually revolves around this. It will execute the virus, but in a sandbox. In a way, a sandbox is basically an isolated environment, and the OS or the other programs, other processes won't get affected. So it's basically preventing the virus to run from the actual environment, actual operating system environment. So most of the work has gone here. So that is what they mean. So because it is hard to predict if an execution is benign or not. Roughly speaking, most of this activity falls into 2 categories: efforts that attempt to guarantee the integrity of control flow in existing programs, and efforts that attempt to isolate bad code that has been introduced in the system. So examples are type-safe languages, stack cookies, or here it's WXRX, memory tainting, virus scanners, and most of trusted computing. So here what they're trying to tell is so let's talk about the attempt to isolate bad code that has been introduced to the system, because it actually links with something we have discussed it here before in the abstract. So we were talking about an attacker who has crossed the network security software like firewalls, IDS, and who has access to the server. Now, what can we do? What can we do to fail his exploit, to fail his attacks? How can we do that? So, most of these techniques fall under that category. Once the code has been, suppose the attacker injects malicious code, how do we make sure it fails? how to fail it. So that is when all these all these security techniques come in. WXRX, memory tainting, virus scanners, most of trusted computing. So WXRX, memory tainting, virus. Okay, so memory tainting is basically marking. Okay, so let us take an example, small example. So suppose you have a pointer. Okay, you do this, and then you try to access. So basically what is happening, memory is allocated dynamically at runtime by malloc, and then a pointer is returned to the PTR. Basically the address is stored in the PTR variable. So here there is a link that is made between this memory and PTR. So we can actually paint file new. Okay. So here, so this is a piece of memory starting at an address 0x12345678, and then there is a PTR. So basically there is a table here. Okay, we'll just draw the table without. Okay, this is enough. This is the memory we are talking about, and then all the pointers which has access to that memory, basically which are authorized to access. So from this we can know that PTR is authorized because that code is getting executed. So the memory at 0x12345678, 10, basically the 10 bytes starting from that address, PTR, if PTR accesses this memory, then it's a valid access, there's no problem. So basically they mark, these are linked here. Later if some code like this gets executed, I typecast this char star cptr is equal to char star of PTR. Something like this happens. So here, because this code is valid, cptr becomes an authorized member to access this memory. So cptr is added to this list. So this seems like a really heavy technique, but it's not. I mean, there are solutions for these. I think Georgia Tech came up with dynamic tainting. Tainting is basically marking these. So you mark, say, wait a second. You mark this with a 1, for example, and you mark the PTR. PTR has 1 and cptr has a 1. So if some other pointer tries to access it, so the taint marks, they're called taint marks. If the taint marks doesn't match, then the program is probably killed. It's terminated because it's a sign of illegal memory access. So okay, this is the paper. Yeah, okay, we'll just effective memory protection using dynamic tainting. So that's what they're talking about. Okay, programs when memory is allocated at runtime. Our technique taints both memory and the corresponding pointer using the same taint mark. So it's something similar. So you basically mark this and this with the same mark, and then later if a new pointer comes in suddenly and then tries to access some location which doesn't have this taint mark, it doesn't have a 1 here, it doesn't have a 1, so the program is probably killed. So here, I think in this paper they have come up with a solution for this. I think a practical compiler based or some solution. So that is a short intro to memory tainting. Virus scanners, antivirus software, which make sure code doesn't get executed at all. Okay, so coming back to efforts that attempt to guarantee the integrity of control flow. So this is also very important. So you can see that, okay, let's actually take this example. So we have our code 1, which is a very simple one, echo program, but something can trigger it to behave in a very different way. So we'll just enter really long string, we'll see what happens. See what just happened? It got crashed. So it says aborted core dumped. So something called a stack smashing detected, unknown terminated. So this was not intended. That is what these help in protecting. They guarantee in the integrity of control flow. We know the control flow. Control flow is this is the control flow and nothing else. But here, based on the user input, the control flow is being deviated. It's being changed. Somehow we are able to crash the program, but it is not supposed to be crashed. So this is a diversion in the control flow. So type safe languages, stack cookies, XFI, these are techniques which help in guaranteeing the integrity of control flow, making sure the control flow is intact and it's not deviated. So we'll talk about a couple of these security techniques later as we go through the paper. So that was the first paragraph. It basically talks about the efforts made in securing a system. The two types. The WXORX protection model typifies this latter class of efforts. Under this regime, memory is either marked as writable or executable, but never both. Thus, an adversary may not inject data into a process and then execute it by simply diverting control flow to that memory, as the execution of the data will cause a processor exception. So here, this these lines are actually describing what WXORX is. So before going to what that is, let us simply witness WXORX in action. So we'll run code 1. Let it be running here. We will go back. Just reduce the size a little bit. So here we will take a look at code 1's address space. So PID is this. So you can look at the address space, basically memory layout at /proc/PID/maps. 17173 is code 1's PID. So that's what we are doing. Okay. So look at this. So first, this is, don't worry about what these things are. We'll come to those slowly. But basically, look at these security permissions for each of these memory address ranges. So in the first address range, it's R-X. Basically read, no write, and executable. Here, the second one, it's read, no write, no executable. Basically, it's a read-only address space. Here, it's a read, write, and a no executable. It's only read and write, no executable. So you can see that every address range has similar permissions. What they try to mean in WXORX is the word WXORX stands for this. We'll come out of this. We'll go back to our beautiful scratch pad. So WXORX So this is basically a security protection. What does XOR mean here? So if W is 1, basically, so in the end, output should be 1. That is the goal. That is the goal, right? So if W equals 1, then X is forced to be 0. Right? You know how the XOR operation works. 0, 0, 0 XOR 0 is 0, 1 XOR 0 is 1, 0 XOR 1 is 1, and 1 XOR 1 is 0. So they both should be different. So if X equals 1, W is forced to be 0. Forced to be 0. For the output to be 1. What does the output 1 actually signify? It implies W XOR X security technique is in place. So what exactly does this mean? We will come to that. So what I can tell you at this point is, you take any security, you take any address mapping here, you won't see RWXP. W and X will never be together. There is no address range where it can be both written and can be executed. It can be either written or executed. And read is always there for either of them. I mean, that's the fundamental thing. If you want to execute something, you need to read it. If you want to write something, you actually need to read it. So write and execute are not together. So how will this help? That they have showed a small. They have actually explained it here. So the W XOR X protection model typifies this later class of efforts. Under this regime, memory is either marked writable or executable. Wait a second. Okay, I hope you are able to see the paper properly. So it'll be easy to read the paper and then do stuff on the terminal. So, so that's what they're telling. Either it can be marked writable or executable, not both. So that's what we were talking about. You will never see a RWX. No, that you won't see that in a normal in modern operating systems unless you force it to be. You can force it to be for an address range to be both writable and executable, but by default it will be either writable or executable, but never both. Thus, an adversary may not inject data into a process and then execute it simply by diverting the control flow to that memory, as the execution of the data will cause processor exception. So here they are actually talking about an old traditional technique called the code injection exploitation technique. So here the idea in this code injection was basically you put in some code. So the buffer we were talking about, buffer of 100, you put malicious code here, then jump to that code. Okay, we'll take a more practical example. So this is the buffer. Initially nothing is there, and then the getS will get executed. So there we will put in some machine code. Okay, we actually have example of machine code right here in code1.obj. We'll put in actually some machine code, say 53 0x53 0x83 0x EC 0x008 0xe8. Say we put this machine code. Later jump to this using something like this, jump buffer. Then what will happen? The control is actually transferred to the code we injected. Injecting is basically you inject the code and then you jump to that code. Inject is a fancy word for inputting it. You inject it because it's, I don't know, it's malicious. So you inject some unknown code, and then you jump into it. So here, because the user has injected it, and we jump to it, it gets executed. So what were we talking about? Integrity of control flow. So we know how the control flow should go. It's very simple. Main, first printf, then the function, and then take the user input, give back the user input to the output, print it back, and then print the second printf. So that was what the control flow was. But here something very different is happening. We are able to execute integrity of control flow is lost. We are able to execute user input, or fancily called injected code. This was never the plan in the first place, because the program was never programmed to do this. So we will actually demonstrate the code injection exploit technique in a while, I think in the second section. For now, just understand that it's an old exploit technique which was useful to get control of the system after the integrity of control flow is lost, after it has been deviated. Yeah. While the security community understood that WXRX is not foolproof from these techniques, actually return to Libc is one of them. Return to Libc breaks WXRX. So I think in one of these, I think this return to Libc, in this paper, return to Libc was described. So it was thought to be sufficiently strong mitigation that both Intel and AMD modified their processor architectures to accommodate it, and operating systems as varied as Windows Vista, Mac OS X, Linux, OpenBSD now support it. So that was the kind of impact WXRX had. So it was not foolproof, but it was really effective. It was effective in most cases. So it was deployed across operating systems and in two of the very popular processor architectures. In this paper, we present a new form of attack dubbed, also known as, return-oriented programming that categorically evades WXRX protections. Attacks using our technique inject no code, yet can induce arbitrary behavior in the targeted system. So here, after the integrity of control flow is lost, we had to execute user injected code, basically some code like this, to get control of the system. But here, in ROP, there's no need for code injection. We can easily induce arbitrary behavior without the need for code injection. We will see how this can be done. That's the crux of the paper anyway. So that evades WXRX protections. This also breaks, defeats, bypasses the WXRX protection. So that is one more. Sorry. So okay, so we were here. I'm sorry. So this also breaks WXRX. Instead, our technique aggregates malicious computation by linking together short code snippets already present in the program's address space. So before, either we had to inject user input, we had to inject some code, or we had to make sure some virus runs. So either of them. But now they're telling that our technique aggregates malicious computation by linking short snippets together that are already present in the program address space. So the address space is actually this. We'll actually go back to that address space. We'll open up a new window for us. Sorry for repeating this. We'll keep this open for a while now. So this is what the process address space looks like. Basically, this is, so you can look at that. This is basically the text segment of the process where the machine code is present. Here, this is the read-only segment where the constant literals are present. This is the data segment where the read-write, the data global variables are present. So this is the heap from where memory is dynamically allocated. So this is the library, the C standard library, which is mapped onto the process address space, right? And the rest of it, so there are other mappings too. It's called VVAR, VDSO. Each of these has a, and then we have the stack, the runtime stack, which is also present. And this is the dynamic linker. So we don't have to worry about this too much. But the point ROP, but the point the author is trying to make is, we don't have to inject code. We don't have to run a new virus. We can use instruction sequences already present in the address space. So there is a lot of code present in this address space. This is the text segment. It definitely has a lot of code. This is the text segment of the C library. You can see that it's read and executable. So this is supposed to be the text segment, and then this is supposed to be the text segment of the dynamic linker. So there is actually a lot of code present in already in the address space. The ROP will just make use of these instructions and induce malicious behavior. It doesn't have to inject code or a virus or run a virus. How exactly is it planning to do that is the paper. That's the paper. Okay. Instead, our technique aggregates malicious computations by linking together short code snippets already present in the program's address space. Each snippet ends in a RET instruction, which allows an attacker who controls the stack to chain them together. Because the executed code is stored in memory, marked executable and hence safe, the WXORX technique will not prevent it from running. So here a lot of so this actually summarizes the technique of ROP. You may not let us not think too much about this because it is hard to understand just by this one paragraph. So we'll skip this. We'll come back to it later. Yeah. The organizational unit of a return-oriented attack is the gadget. Each gadget is an arrangement of words on the stack, both pointers to instruction sequences and immediate words that when invoked accomplishes a well-defined task. So when let's take a look at the stack now. Okay, new one. So this is how the stack looks like. Runtime stack. I'm talking about the runtime stack. Sorry about the. Okay. Okay, we are good to go. So this is pointed by the this is the stack pointer, right? So what they're telling is okay, so we are able to see the stack, right? So the organizational unit of a return-oriented attack is the gadget. Each gadget is an arrangement of words on the stack. So this is the stack and it is an arrangement of words. So this is one single word. If the width of this is, say, in a 32-bit Intel system, it's 4 bytes. Stack width 4 bytes. If this is 4 bytes, one word is actually 4 bytes in size. So that is a very fundamental unit when it comes to a processor. So each of these words on the stack, say this is the word 1, the word 0, okay. Word 1 is word 2, sorry. There's the word 3, etc., etc. So what they're telling is either these words can be a pointer to an instruction sequence, or it can be an immediate data word, which then that when invoked accomplishes some well-defined task. So at this point, understanding what this actually means is a bit hard. So we'll actually we'll skip this too. The technique has been well described in the later parts of the paper, after which we'll come back to this. You'll be able to understand this really easily. So, okay, one gadget might perform a load operation, another an XOR, and another a conditional branch. Once he has put together a Turing complete collection of gadgets, an attacker can synthesize any malicious behavior he wishes. We show how to build such gadgets using short instruction sequences we find in target binaries on both the x86 and the SPARC architectures, specifically the standard C library and Linux and Solaris respectively. So they take up two very different architectures, and they try to build gadgets using short instruction sequences. So we actually took a look at what a short instruction sequence means. So let's go back. Sorry. So we actually took a couple of examples here. So it would be this pop ebx, ret, or anything ending with an ret instruction. That was what was given in the abstract of the paper. So anything ending with ret. So there is this here. Oops, sorry. Whoa, where the whole thing got cut. So there's a move, blah blah blah, and then ret. So using these short instruction sequences present in the address space itself, it could be present in the text segment of the program, it could be present in the text segment of Libc, it could be present in the text segment of the dynamic linker. Code1 was a very simple program just for the sake of demonstration, but other complex programs have a lot of libraries mapped to them. So not only the C standard library, but a lot of other libraries. So code segments of the instruction sequences from those new other code segments can also be used by this attack. We show how to build. Okay, this is okay. They use the standard C library specifically on Linux and Solaris respectively. We conjecture from our experience on two radically different platforms that any sufficiently large body of executable code on any architecture and operating system will feature sequences that allow the construction of similar gadgets. So here they have demonstrated the attack on x86 and SPARC, but they conjecture, they hypothesize that this attack can be used on any other architecture and operating system with a large body of executable code. So this is necessary. This is a necessary condition. With this, they tell that ROP can be exploited. ROP can be used on other architectures too. Okay. So these are the contributions they've made. Our paper makes 4 major contributions. We describe efficient algorithms for analyzing a target library to recover the instruction sequences that can be used in our attack. In our x86 variant, we describe techniques to discover unintended sequences by jumping in the middle of other instructions. So they describe algorithms to recover the instruction sequences, the RET ending instruction sequences, which can be used in the attack later. Using sequences recovered from the target libraries on x86 and Spark, we describe gadgets that allow arbitrary computation, introducing many techniques that lay the foundation for return-oriented programming. So first is the construction, gathering of such RET ending instruction sequences. You know what an instruction sequence is? It's basically a series of instructions. Later, building something called a gadget, which allows arbitrary computation. Okay, so this is the order. Later, once you do this and using these RET ending instruction sequences, you build something called as a gadget. We'll see what a gadget means in a while. So we discuss common aspects of gadget construction and return-oriented attack we discuss common aspects of gadget construction and return-oriented attack structuring and injection across two popular architectures. Okay, that's known. Now we demonstrate the applicability and power of our techniques with a generic gadget exploit language and compiler that simplify the creation of general purpose return oriented program. Okay, the fourth one is basically trying to automate the exploit technique. The three was these three demonstrate the attack on the two popular architectures. The fourth one will try to automate it, make it easy for testers and even attackers to create return-oriented programs in order to exploit vulnerability. We challenge the flawed but pervasive assumption preventing the introduction of malicious code is sufficient to prevent the introduction of malicious computation. So this is what we were talking about. This assumption that this is the implication we were talking about back then. So we told that preventing introduction of malicious code, basically virus or injecting it, is sufficient to prevent introduction of malicious computation. This was the basis, the implication on which many software was built. But now they are challenging this implication. They are telling that this implication is flawed. Implies they can with ROP we can break this. You can break this implication. Okay. By the means of return-oriented programming, an attacker who has subverted the control flow of a program can induce arbitrary computation without injecting any code. I think they've repeated this too many times. I think just for it to sit in our mind. I think this is the third or fourth time just from starting from the abstract. So I hope you get the point. Without injecting any new code, any new user code, one can induce arbitrary computation. That is the idea. Because it applies to two very different architectures and can be abstracted and automated into a general programming framework, we argue that return-oriented programming is a usable, powerful, that is Turing complete, generally applicable threat to systems assumed to be protected by WXRX and other code injection defenses. So now they're talking about how powerful this technique is, and they have come up with a general programming framework. They have automated the exploit generation, so that's cool. Protected by WXRX and other code injection defenses. So they are going to get broken. So now we'll talk about some previous publications. Two extended abstracts by present authors introduced return-oriented programming on the x86, Sasham 2007 and Spark in 2008. So that's what I was talking about. The first paper about return-oriented programming was published in 2007. The one we are reading is, I think, was published in 2010. So the first came in 2007, exploiting the x86 systems. So the present full paper, this one, supersedes both these previous publications and is intended to be the definitive statement on return-oriented programming. Return-oriented programming. Much work has followed up the conference publications that make up the present paper. Besides the x86 and SPARC, return-oriented programming has been extended to the Atmel AVR, it's one more architecture, instruction set architecture, PowerPC, Z80 and ARM architectures. Gadget creation has been partially automated by so and so people. Return-oriented programming has been used to attack platforms where WXORX cannot be disabled, including the Sequa AVC Advantage voting machine. I don't know what this is. I mean, it's obviously one more machine running some software which has a strict WXORX protection. That is what I can understand. And the iPhone. Defenses have been proposed to return-oriented programming that depend on its use of return instructions by so-and-so people. These are defeated by a variant of return-oriented programming that uses no return instructions. So the first paper was, it came out in 2007. After that came out, a lot of research, I think a lot of researchers started, discussing and exploring different possibilities of return-oriented programming, different possibilities around return-oriented programming, its variants, defense mechanisms which can help mitigate ROP exploitation. So they are basically listing all these. So these are defeated by a variant of return-oriented programming that uses no return instructions. More comprehensive defenses remain unbroken, but approach control flow integrity in complexity. In an important development, return-oriented programming has been embraced by the industrial security community. Much work on return-oriented programming is being conducted outside of traditional academia venues, and return-oriented support has been incorporated into commercial tools such as the Immunity Debugger. Immunity Debugger is a famous debugger used in Windows. So there's ROP support there. I think ROP support is there in many debuggers. Even in Radar 2, there is an ROP chain, ROP support module. So okay, any comments? Okay, so we have a comment here. So they want me to move a little bit faster, maybe skip a couple of topical introductions. So okay, I think we can do that. I just don't want later when we will have to go into these techniques. So okay, I'll just drink some water. Okay, background, attacks and defenses. We'll read through it a little bit faster. I have planned for one or two demos here so that we can understand ROP better later. So with return-oriented programming, an attacker who has diverted a program's control flow can induce it to undertake arbitrary behavior without introducing any new code. This makes return-oriented programming a threat to any defense that works by ruling out the injection of malicious code. So the necessary condition for ROP to work is an attacker who has diverted a program's control flow. So already diverted program control flow. This is an important necessary condition that can be used, and it can be used to induce control flow can induce it to undertake arbitrary behavior without introducing any code. Okay, so this makes return-oriented programming a threat to any defense that works by ruling out the injection of malicious code. A notable example of this class of defense is WXOR X, widely deployed on desktop operating systems to make memory errors more difficult to exploit. In this section, we focus on the implications of return-oriented programming on WXOR X as the natural natural next step in a series of attacks and defenses whose history we recall here. So this is what I was trying to tell in the beginning. So there is some program and there is a vulnerability. So one tries to attack it, basically come up with a new attack exploit mechanism, and then the defensive community comes back with a defense mechanism, and then to break that defense mechanism, the offense community comes up with one more attack. So it's a series of attacks and defenses. In particular, return-oriented programming can be seen as a generalization and refinement of the return into Libc attacks, in which the attacker's power is increased at the same time that the assumptions made about the exploited environment are reduced. So here they talk about two things. One is it's a generalization of return to Libc. Second is a lot less number of assumptions are made. So both are a plus in this. It's a win-win here. Okay, consider an attacker who has discovered a vulnerability in some program and wishes to exploit it. Exploitation in this context means subverting the program's control flow so that it performs attacker-directed actions with its credentials. So that is what exploitation means. It can perform attacker-directed actions with its credentials. Basically, whatever the attacker tells, the exploited program should be able to do it. The most familiar such vulnerability class is the stack buffer overflow. Though many other classes have been considered, such as buffer overflows on the heap, integer overflows, and format string vulnerabilities. They're all really popular, infamous, very dangerous vulnerabilities if present in a program, because a lot can be done. An attacker can take complete control of the system if these are present. So I think we specifically will take stack buffer overflow as an example in most of the demos and programs we take, and then explain. So to achieve his goal, the attacker must 1. Subvert the program's control flow from its natural course. So that's what we were talking about. Basically, the defined intended behavior should be diverted. Deviation from defined control flow. That was one. And second, redirect the program's execution. Redirect. So first you take control of the control flow, you divert it, and then redirect program's execution to anything the attacker wants. In traditional stack smashing attacks, an attacker completes the first task by overwriting a return address on the stack so that it points to code of his choosing rather than to the function that made that call. So okay, let me read this again. In traditional stack smashing attacks, an attacker completes the first task, that is the deviation from defined control flow, by overwriting a return address on the stack so that it points to code of the attacker's code choosing rather than to the function that made the call. So here let's take an example to understand this, what they mean. I think it's fair to spend some time on this. So this is the program we had considered before. Let's modify it a little bit. We'll add one more function here. Let's call it not reachable func, and let us take a print statement. This should not be executed. So let's run through the program. So we start with main. Main does this printf thing, and then it calls func. Func takes in the buffer, takes in the user input, gives back, and then comes back. No way here that this function can be executed. So in normal defined control flow, this can never be executed. So that, I hope that is clear, because that function is never called anywhere. Okay, so let us compile it. Okay, to compile this, we will have to disable certain security measures for this demo. So if you are following me on this, okay, I'll just clear this off. If you are following me on this, you can use these flags. F no stack protector. This is a security measure which will stop whatever we are doing, but let us disable it for the sake of the demo, right? And we will execute it. We'll compile it. So there we go. Okay, along with that, I think we also have to disable one more security measure. It's called the ASLR. It's called the ASLR, address space layout randomization. We'll come to that later. I mean, why it's a really effective security measure. For now, for the sake of demo, let's just disable it. You can do it this way. So echo 0 randomize VA space, virtual address space. So let us echo a 0. So basically there are 3 values here in the implementation: 2, 1 and 0. 0 is basically disabling it, which will help us in which will help us in the demo. Okay, so now we'll run the program. Okay, nothing will happen. That's a very simple straightforward echo. But once we try to input longer inputs, okay, so we'll use Python here, which is very helpful in generating long inputs really easily. See, we had defined a buffer of 100 bytes, so we'll take say 120 and then pipe it to code 1. So here it's like faulted. Something is happening. So let us just go through in short what's happening. We'll break at func because that's where it could be happening. Run. Okay, so you need to understand that in x86 architectures, the arguments to a function are pushed onto the stack. So getters takes one argument, which is the address of the buffer, and that is being pushed here, push EAX, and which is being executed So this is the address. So just make a note of it. In the end, we will be writing an exploit, so we might as well start writing it now. So this is the address of the buffer. Then later you go ahead and execute it. Execute getS. So you enter something. Then later, so we can check this address. What is the data present in that address? Say the buffer was 100 bytes, right? So we will dump 100 bytes. So this is a byte by byte view of what's present. So we entered something, and then later it got executed. We are returning back here. We are returning back to the main function, and we are back to main. So this is a normal straightforward execution, but we saw it crashing for a really large input. So what happened there? That is what we need to see. We'll just run through it again, and so this is the stack. So we'll dump about 120, 130 bytes. Okay, there's already some stuff here, don't worry about it. So after, okay, now this view is, wait a second. Okay, before coming to this, let me explain how this thing works. Memory, how data is stored in stack. So this is the stack. So here is our buffer. Okay, so here is our buffer, and we fill in 100 bytes, and then later down there is something really important which is of use for us. There is the return address to which the function has to return back to. So you can see that once the main is once the func is executed, it has to go back to main. Where should it go back to main? So this is func. Once this returns, it has to go back. We can take a look at main's disassembly. So here is the call to func, right? So this is a call to func, and once func is done, it has to come to this address, right? Can you see this? 0x56ffff5555df. This is the address it has to return to. So this needs to be stored somewhere. The callee, the func function needs to know where to jump to. That is actually stored in the stack, right? So if we take a look at the stack now, we'll just xd word, no, x quad word, x word, right, sorry. Okay, that's a lot of words, but after 100 bytes, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 16 into 8, 128. Okay, so you can actually see the return address here. If you look at this, it's actually stored on the stack here. So idea is, once we are while we are inputting data, we'll input all trash here, and we'll input the address we want here. So we'll try to do this. So the gap between okay, we'll just return stack address is, say, this, right? Sorry, buffer address is this. So the gap between them is buffer is return stack address minus buffer address. Okay. Let us define payload as some nothing in the beginning, and then payload some random bytes which fills the gap. So let us write it to a file, right? Payload.txt. We are writing bytes, so f dot write payload f dot close. Okay, that's where we are. We will execute it. So the payload.txt has the input to this program now, right? So we can run with the payload.txt as the input, right? So it won't ask us for the input now. It will just take in what is given from the file, right? So let us inspect the stack again. Say let's take 5xw and the buffer. See, they're all 0x61 is basically the ASCII equivalent of small a. There are a bunch of them, and then something has happened here. See, look at this. This was the return address. So if you remember, it was 0x565555df or something, but the 00 is basically the null character. So what we have done here is we have written into the buffer and we have tried to override the return address. We'll just continue the execution. So it's segfaulted. Look at this. It's segfaulted. The reason being, let's take a look at the EIP, right? So look at the instruction pointer 0x56555500. This is the modified return address. This is not the original return address. The original return address is supposed to be this. Where is func? This. It's supposed to be 565555df, but it's 00 because of the null character which came in at the end of the string. So now we are able to write whatever we want in the return address position of the stack. So what do we want to execute now? We want to execute this. We want to execute this non-reachable function, which will never be executed in a normal control flow scenario, but now we want it to be executed. So let us go ahead. We know its address. Let us go ahead in the exploit and then write it up. Okay, this is a very useful library, I can say. Payload is now not just the trash. This is basically the junk. Not just the junk, but also the return address at the end. We need it in the Little Indian format because Intel follows Little Indian architecture, and then the number. Okay, so there we have okay, so we can go ahead and exploit. So now payload has more than just a. So till here it's the buffer, the string, whatever, and then here is the return address, the possible return address. So let us run again with payload.txt, right? Then we'll continue. Okay, before we go ahead, I want you to see that okay, I think the return address, I think the code has been placed in okay, so this is the return address. So let's go ahead. Okay, let's check the stack ones. 50xw starting from the buffer. Oh, I'm sorry, I think I copied the return address itself. I'm really sorry. Not reachable func. So we had to copy this, the starting address of this. So so I hope I made a mistake there. I just want to clarify that. So I took the actual original return address. Basically, I took this, which is the original return address, and put it in the exploit, which is not correct. I mean, we'll jump back to the same. The control flow will not be deviated. So instead, we wanted to take this, which is basically the first address of the non-reachable func. We have taken that, and let us run it. Okay. We ran it. So now the payload.txt has the new return address. So payload.txt. Okay. We'll go ahead. Go. 1. Okay. Okay. This is W. Let us see what it's. So here return address, it basically the return instruction takes the topmost stack value and then jumps to that. The topmost stack value is here it's being shown as a string. It's actually the wrong representation. It's an address. It's 56555540. So let us go ahead and execute this. So now we are in the non-reachable func function. So with what I wanted to explain with this is, in normal control flow, the intended control flow, this function we could never execute this function, but because something because we were able to input inputs longer than the buffer, the size of the buffer, we were able to do this. So what we did is basically we overwrote as they mentioned here, coming back to this, in traditional stack smashing attack, an attacker completes the first task by overwriting a return address on the stack. So I'm repeating myself. So this was the return address, and on the stack it was supposed to be this. So we enter something. So just want to so this is the buffer. And this was where the old return address was placed. So it was supposed to be 565555DF or something, but here it's 4D. We have overwritten the return address on the stack. That is what this sentence actually means. So that it points to the code of his choosing rather than the function that made the call. So instead of going back to main, which was the actual caller, the function that made the call, we are going to the code I want, basically the not reachable function. So that is how the control flow was deviated. That is what I wanted to explain with that. Is this clear? If someone is listening. Hey, sure. Huh. So we used, let's clear this off. Okay, so here we are using a couple of flags. -O stands for output, nothing more. -M32 is basically, so this paper deals with the x86 architecture, which is the 32-bit Intel architecture. So because I am running a 64-bit system, I need to use this flag to generate 32-bit executables. That is what M32 means, machine 32. M stands for machine. -G will basically help in debugging. It will add debugging symbols inside the executable. It will help the debugger. It will help us in running it better. Analyzing it better. -F no stack protector is basically, there is a security mechanism called stack protection or stack canaries. So we are disabling it. -flag no stack protector. This is basically because, just for the sake of demo, with that security mechanism we couldn't demo it. It will crash the program and we couldn't show the we won't be able to show the control flow deviation to non-reachable func. So with this flag on, without that protection, we will be able to show the demo. So that's, I hope it's clear, right? Oh, coming back to the paper, so that it points. Okay, this is all done. Okay, though even in this case, other techniques can be used, such as frame pointer overwriting. I have not really explored frame pointer overwriting, so I'll just leave it, skip it. He completes the second task by injecting code into the process image. He points the modified return address on the stack to this code. So this is where things get really interesting. We witnessed the first part. Basically, we had full control of the return address on the stack. We could write it with anything, not only a valid address. We could write it with an invalid address too. We could write it with say 0x12345678. It may not be valid, but we still have control over it. So we have full control. We have all the liberty to write it. So the first part is over. The second part they're talking about is he completes the second task by injecting code into the process image. So I'll take a small detour and explain what code injection is along with the demo. So to inject code, let us inject very simple. Okay, move EX. Okay, I hope you know what a system call is. System call is basically an API offered by the operating system to use a particular resource. There are system calls like write, which will help you write into a file, or the standard input or standard output or standard error, or the read, which helps in reading. There is exit, which will kill a process, which will terminate a process. There is exec VE, which will help in spawning a process. Fork, etc. Okay, actually fork helps in spawning a process. Exec VE will bring in a new process in. So fork will make a copy. Exec VE will actually run the new program. So these are a couple of system calls. They are all provided by the OS for us to access its resources. So here we'll just execute exit system call. Where is the scratch pad? Okay, here is the scratch pad. So the exit system call. So here, to execute a system call, there is a couple of rules. The rules are something like this. So the register EAX in the x86 architecture should have the system call number, which is 1. Exit system call number is 1. And then EBX should have the argument, basically exit of argument. And that's it. And then we request the operating system, request the OS to run the system call. So I'm telling you, we need to execute this instead of the non-reachable func. So we saw the first one. We are trying to do the second one by injecting code into the process image. We'll try to do that. Let us get the machine code of this first. Move EAX, 1 and move EBX, 0. We'll just do exit of 0, right? Just do an exit of 0. It's just for demo purpose, so it's no problem. And then int 0x80. That's it. So we here, RASM is basically a module in Radar 2. Radar 2 is a really awesome reverse engineering framework. So it can help you with all this small, fast way of doing things. So we got this machine code here. So we need to store it somewhere, right? We will, in the exploit, we'll just B80x01x00. Okay. Sorry. CD 0x80. Right. So this is in the byte format, bytes. So this is the machine code. So what they're telling is this machine code should be present in the image. We need to inject it somewhere and do it. So where do we inject this machine code? Where do you think we can inject this? We can actually inject it into the buffer itself. The buffer, anyway we are storing it with junk. As well we can actually store some machine code and then fill it up with junk. So we can start with this is no longer true. We start with an empty payload and we add machine code to it, and then we add junk. How much junk should we add? Gap minus len of machine code. Basically the gap is the same. Because we have filled the first few bytes with machine code, the rest of the bytes we need to fill it with rest of the bytes we need to fill with crap. Okay, with junk. I'm sorry. So here, okay, for now we'll just write in some weird address and then let it crash. It's okay. With that we are ready. We'll run it. So the payload.txt now has the code 1. Okay. We can run. Okay, I'm sorry. We'll run it with payload.txt as input, right? Run, execute the getters. Now we'll take a look at the buffer. say 100. So we'll take 50 XW of this. So you can see the machine code here, B8010000 00BB0000. Okay, they're all stored in the ulta, in the reverse format. That's the essence of little endian, but don't worry about it now. And then later, once the machine code is over, the 12 bytes, there's crap all over again. So let's so machine code, junk, and then the invalid some number which we gave. So we'll make sure it jumps to this address, to the 0x12345678, right? And then we'll confirm that it's working that way, and then okay, I think I made a mistake here. Payload is blank. Payload, you add machine code and then gap minus none of machine code. Okay, shit, I had to delete this. Sorry guys, sorry, I'm really sorry. We'll just run it over again and then we'll just quickly verify that it's working, right? So we'll just go to RET. Yes, so if RET gets executed, an instruction, a potential instruction present at this lame address should get executed. So look at this, EIP is loaded with this. So now we have, we know that we have control of EIP. What do we need to do? We want to execute this machine code. So where do we need to jump? Where is the machine code stored? It's stored in the buffer. So we need to jump to the starting of the buffer, right? With that, we will be done with so instead of this, we need to put the address of the buffer. So getting the address from GDB is one idea, but it may not work. So this is actually the address of the buffer in GDB. Sorry, in GDB. Okay, we already have stored it somewhere here. Buffer address is this. So we'll put the buffer address and then go ahead. So we'll run it again. Run payload.txt. Right. So we go. And there you go. So here, this is the buffer and it's pointing to some 2 bytes of machine code. We will do an NI, the next instruction, and we are somewhere here in the stack. See, look at this. This is the buffer and we are actually in the stack. We are trying to run this machine code. You can look at this. We can disassemble. We can get the, say, 12 bytes at this address. So it's what we think it is. See, B80100, it's the machine code we injected. We'll try to execute this instruction and then see what happened. It actually segfaulted. So why the hell did it segfault? It's pure machine code. We know that. It's a simple exit system call, exit of 0 system call, but it segfaulted. Why do you think it segfaulted? Any idea? Any thoughts? Okay, so the idea is this, that we are going back to what made this stop is what we were discussing about, is the W XOR X protection. So we'll just stop here, right? we'll come out of this exploit thing, right? We will run this again with payload.txt, right? And then we will go ahead, do all that this, and then we are here, like right before we execute the instruction. So this is the stack, right? So we'll get the PID and look at the stack's permissions in the mmaps file. With this is the permissions file. This is all this. Look at this. This is very important to understand. Here there is a read, there is a write, but there is no execute. So we are trying to execute something on which, I mean, it's just not executable. So whatever is there on the stack, you can't execute it. You can either read it or you can either write into it. That's it. So that's why it's at faulted. There is a rule in place which will not allow you to execute injected code. This is what they were trying to tell. I'm sorry. The paper. Yeah, back to the paper. Where is this? He completes the second task by injecting code into the process image. So I think the task can be completed if this security permission was removed, if it was not there. So we'll try to remove it and we'll execute it again. So we'll come out of the debugger, right? And then we will try to. Okay, so one more thing about security protection is you can secure it only if you want to. So that is a rule followed here. So you can request. There is a tool called, I hope you are able to see this, called exec stack, which will set the stack to be executable. Set executable stack on code 1. Sorry. What? Okay, sorry. Set exec stack, right? So with that, this will no longer be read write. It will be read write and execute. So let's check it out. We'll just take we'll do a debugging session again. Just set a breakpoint first. Run payload.txt. Go, and we're here. We are just right before executing it, and we do an NI, and then it gets executed. See, we are on to the next instruction. Run, it's done. Now we are about to request the OS, it's done, that's it. The program was killed, it exited normally. So the exit of 0 got executed successfully, and it was the program was terminated. So what the point I'm trying to tell is done. So coming back to the paper, sorry, should I keep coming back to Firefox? So he completes the second task by injecting code into the process image. So here we took a very simple example, which is executing simple machine code, simple exit of 0, but that is definitely some kind of arbitrary behavior. But more powerful thing would be to take control of the system, get a shell, and try entering any command, and that command should be executed. Basically, getting a shell is more powerful, obviously. So that will probably be the end goal of anything. You get a shell and you can enter any command, so that way you have control over the system, right? So we'll come to that later. We'll come to getting a shell later. So I hope you understand these two techniques, because it's very important going through. So there are two things. One is overwriting a return address on the stack and take control of the control flow. Second, injecting code into the process image. Redirect the So those two are the important things. Okay. For historical reasons, appropriate code to inject is called shell code, whether or not it spawns a shell. Yeah, I think they started with spawning a shell, and then later, even exit, we entered about 12 bytes of pure machine code. Excuse me. I don't know. Okay, that's my mom. So we input 12 bytes of machine code, and we are able to run it. Although it doesn't spawn a shell, even that is called shell code for some reason. Okay, let's continue. In this paper, we restrict our attention in the attacker's second task above. That is, the second task was redirect the program's execution. The first was subverting the program's control flow. That is okay. And then second is redirect the program's execution. This paper will be about the second one, redirecting the program's execution. There are many security measures designed to mitigate against the first task, each aimed as a specific class of attacks, such as stack smashing or heap overflows, and we briefly consider their implications for return-oriented programming in section 2.2. So I'll just take a small, okay, there's no detour, but so what I was, I'm glad you asked about the, compiler flags, because this is a point where we can actually, make a point. So this as I was telling, this was a security measure to make sure I don't deviate the control flow. In the sense the attacker doesn't deviate the control flow, but this is one security measure. It's quite effective. Okay. An important defender's gambit focused on making the attacker's second task harder. So even if you divert the control flow, redirecting the execution or running machine code, just by making it harder, you can fail the exploit. So as we were talking about this somewhere up, so coming back to this, so attacker has access to the server already. So now we can actually make more sense of this. Fail his attacks. Attacker injects malicious code. We actually injected some code into some process. How to fail it? WXRX was one of them. See, it actually didn't allow code on the stack to execute. Memory tainting, even that wouldn't have allowed, because we access from an unmarked this thing, and virus scanners, that will totally prevent it. So failing, okay, making exploits harder. So this is a large part of defense. So when the attacker already has access to the server, all you can do is make the exploit fail somehow, some mechanism. So that is what they're trying to tell. An important defender's gambit focused on making the attacker's second task harder. The earliest iterations of such a defense, notably Solar Designer's Solar Patch, modified the memory layout executable to make the stack non-executable. So this is what we were talking about. The stack was made, so probably in the beginning it was RWX, it was read, write and execute. Later with this patch, the stack was made non-executable because to defend against these attacks. Since in stack smashing attacks the shellcode was typically injected onto the stack the way we did, this was already useful, really good. A more complete defense, dubbed WXOR ensures that no memory location in a process image is marked both writable and executable. With WXOR there is no location in memory into which the attacker can inject code to execute. So WXOR is like a generalization of this stack non-executable thing of this one. So we have two scenarios: stack or some memory where you store data and then you try to execute it, or there is instructions and you write over it. You execute something and then you write over it. So we have two scenarios. so those are the two scenarios. So we saw the first scenario to be in some good detail, basically executing data, executing on a write region. But how do we write into an execute region? Is it even helpful? So the execute region is basically the text segment in all the whatever we saw. The text segment of the, it could be the text segment of the program itself, or the libraries, or the linker, or anything. So is it helpful writing into an execute region? What do you guys think? Okay, it was helpful once upon a time. I actually read about this. So back then, when there was really less memory, say memory was in terms of KBs in the beginning. So it was 1 KB, 2 KB, 5 KB, 10 KB. So once a certain part of the program was done with execution, and the programmer knows that that part would never get executed later, that was overwritten with new instructions at runtime by the program itself, so that you save with the less amount of memory, you can execute more code. So that was the idea. So writing into an execute region was actually helpful back then, but now I think I can but now there is no scarcity for memory. We have a lot of memory. Memory is actually very cheap, but now, yeah, I mean, you can actually think of malicious bringing in malicious behavior. Suppose where's the program? We'll just go to func. So I'm just giving an example. So once getAs gets executed, we can just try writing. If we try writing into this, if we overwrite these three instructions, instead of executing add, sub, and lea, which are the original instructions, our malicious instructions will get executed. So that is actually bad, right? I mean, so writing into an execute region can actually bring in malicious arbitrary behavior. So that was, so they generalized it. WXRX is the generalization which won't allow either of them to happen. So that is good. The PAX project has developed a patch for Linux implementing WXRX, PAX team, blah blah. Similar protections are included in versions of OpenBSD. AMD and Intel recently added to their processors per page execute disable, NX in AMD parlance and XD in Intel parlance. I think NX stands for no execute bit. So whenever a page is loaded, and I'm trying to page is loaded, so there is always a bit which tells no execute bit. Either you can't execute it. If it's set, then you can't execute it. XD stands for execute disable in Intel. They're both the same, just different names. Bit, a per page execute disable bit. To ease WXR implementation, and Microsoft Windows as of XP SP2 implements WXRX, which Microsoft called DEP. So DEP is data execution prevention. You can see why it's called data execution prevention. Basically, buffer was data, and it was supposed to be a place where we store data, but we stored some machine code and ran it off. So it's supposed to be, so data execution prevention makes sense on processors with NX XD support. Okay, the attackers responded to code injection defenses by reusing code already present in the process image they were attacking. So this is something really interesting. So once WXRX is in place, that machine code injection won't work anymore. We just saw it. So it won't work anymore. So they responded. They responded to code injection defenses by reusing code already present in the process image they were attacking. Now we enter. The author introduces a new type of attacks, the code reuse attack. So the standard library Libc was the usual target since it is loaded in nearly every Unix program and contains routines of the sort that are useful for an attacker. Wrappers for system calls. See, we saw system calls are direct gates to access the operating system, so they're really important. and Libc is huge, has a lot of very interesting functions for the attacker. Such attacks are therefore known as return to Libc attacks. I think now is the time where we take small deroute for a demo. We'll see what a return to Libc attack is in short. Okay, and then later continue. Right? Okay. Okay, all set. We are about to see something really exciting. I'm excited. Return to Libc. What is the name? What does the name tell to you? So here we return to our own code. Here we return to our own code, but here we are returning to Libc. So it means that overwrite that return address with some function's address. So this is what it means. Overwrite that return address, the one which we had in control, with some Libc function address, right? So let us try doing that. We'll go back to the same function, the same program, no changes. So we'll break run. So which function do you want to execute now? Which function? Okay, so we'll try getting a shell now. So getting a shell is even more powerful. So we'll just try getting a shell. There are many functions which can fetch you a shell. Very simple. Simplest of the functions are system, which will run any bash command. Run any bash command. And then exec VE, it will basically run a whole new process. It will override this process with a new process, which is also helpful. So you can run shell here. So we'll take a system because it's actually easy. We'll look at exec VE later. We'll actually take up exec VE with ROP. That's actually more interesting. So system. First we will get the address of system. We need the address. We need to jump to that address, right? So okay, we'll start writing the exploit by the way. Okay, I'll be overwriting this. We'll just comment these out. These are not useful. Gap is important. These are not important. Just remove this. It's okay. Okay, so we start with a payload, and then because we are not injecting anything, we can go ahead and go straight with the gap. Nothing more. We'll just fill in the gap with junk, and then later we need to jump to a Libc function. Here we have chosen system, so let us add that. Sorry. Plus struct dot back. Don't forget this. It has to be in little endian format, and then this, right? So system obviously is not a simple function. I mean, it needs an argument. It needs a command to run. What command do we give? So we want to run a shell. So we want to give a shell. I mean, basically the /bin/sh thing. So let us see if we can find the /bin/sh in somewhere in Libc or somewhere in the address space. If it's not there, we can inject it, right? So let us find /bin/bash or sh. Either of them will do. So there is a /bin/bash here. There is also this, right? So we can go with either of them. Let's choose this. So this is supposed to be the argument. So okay, let's go back to the scratchpad here. So it works something like this. The system of /bin/sh. So the argument is basically the reference to the string. Reference is basically this address, right? With that, we can hope we get a shell coming back. Okay, so where do we put this address? How is an argument passed to a function? That is something we need to see. So we'll go back to this paint. This is okay. Okay, we'll actually use this. So there is a return address here, which is basically system. 1 second, we'll draw from here. Say this is the return address, which points to system, right? And this, do we fill the argument here or here? Where do we fill it? How do we, I mean, there should be some rule, right? So the rule is that we need to understand how arguments are passed into to a function. That is what we need to understand. So whenever a function is called, whenever a function, okay, we can actually go back to this. We can break at main, we run it. We will stop just before this, okay, just before we call func, so that we understand what's happening. Yeah. So we haven't called func yet. So the stack address is so and so. Don't worry about it. It is some address. It is some address, and then we call. We go into it. We step in. See, look at this. This is a new GDB instruction command I'm using. Si, step into. I stepped into it, into the function. So what happened? Did you see what happened? So this was the old stack top. The stack pointer pointed to this. Now suddenly there is one more here. Something else is on the top. That is the return address, as we discussed. So whenever, so the return address is on the top, and then we go ahead and execute it, right? We go ahead and execute it. While it's returning, it expects a return address, right? It expects a return address. So here, okay, so here in the stack, so this will actually take us to system, but system is in itself expecting something to return back to. I hope you get the point. System is a function, so it always looks, it has a return instruction in itself, and it will try to return back to. So we should put some crap here, which will return and which will crash, or a valid address which it will peacefully return back to. Either of them. So for now we'll put some trash, and then later we put the argument. This is how a function call takes place. First, I mean, it actually happens in the reverse order. You put the argument, you put the return address, and then jump to the call. So, but here, because we are constructing the basically a fake stack frame, we are doing it in the reverse manner. So this, we'll just comment it out so that it will be helpful. Jumps to system. System expects a return address. So let's put some number there. We don't have to worry about it now. 0x 1 2 3 4 5 6 7 8, and now the argument. What is the argument? Basically the address of bin as such. Okay, where? Okay, we need to find it again. So there is a reason why I didn't use the address of /bin/bash. I'll come to that later. Once we are done with this exploit, I think I need to explain that. We'll come to that. We will put the address here, and with that we are, I think, okay, we're good to go with. So we could have run it from here. Okay, so now the payload.txt has our strong payload. So we will try, okay, we'll clear one. Wait, there's some way to clear a breakpoint. Okay, I don't remember, so we'll just leave it. Run payload. Okay, so we stop at main. We don't have to. We'll continue. We are at function. This is interesting. So getS. Now the payload is in memory. We will take a look at it. Right? x60xw. This. So it starts with trash. That's okay. And then here, instead of the original return address, there is systems address, and then system is expecting some return address, so we have put in some crap here, and this is the address of /bin/sh. So we will go ahead and see if this runs. So okay, it's actually working properly. So if we return, it'll actually jump to system. So we'll continue, see if a shell gets spawned. Okay, so process 2.1 blah 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 is executing a new program /bin/dash. Okay, dash also means sh. It's, I think, a soft link to sh. So that is what we wanted. So we have a new program. We'll try running this on normal. I mean, we'll see if. Okay, let's just try this. It actually segfaulted. We don't know what happened. We actually got a shell here. I mean, even there it was a debugging mode, but here it's not a debugging mode, but we got a shell. I hope you are able to see what is happening. Right? So there are, okay, so I came out of it, it's segfaulted, obviously. So there are two things to explain. Okay, so any doubts so far? That was one moment, we have a comment. So can the session be split across multiple days, or can it be recorded and shared for people? Yes, I am planning to upload this on YouTube. Don't worry. There's nothing to worry about. Okay. So we'll get back. So that was return to Libc. I hope you understood what happened. So system is a Libc function. So we returned to that Libc function, and then we got a shell here. So there are two things to be explained. There are two things to explain. One is I chose the address of /bin/sh instead of bash, because the stack keeps moving because of the debugging, and when you debug, the stack will move a little bit because GDB, I think, puts in a couple of environment variables on the stack. So without, okay, one second, I'll just show it to you. Okay, what I mean is, so suppose this is the address of, okay, this is the address where /bin/sh bash is present on stack. But I didn't choose this because the debugger will generally put a couple of environment variables on the stack. So without GDB, its address would actually change. 0xFFFF. Say it can become 1234. It can actually change. So the exploit may not work. But /bin/, but if it's in Libc, it mostly won't change. because debugger is not doing anything to the library for it to change the address. So that was one. Second was, okay, I think I forgot the second one. Okay, I hope I remember it later. So that was the return to libc attack. We'll go back to the paper. So see, we could have just gone directly to return oriented programming, but I feel that it'll always be better if we know the previous attacks, the prerequisites, the defenses. If we actually witness it as a demo, it'll actually sit, and we can actually understand ROP better. You'll know why. So now that we are conversant with return addresses, stack overflow, and return to libc, what does jumping mean? Where do we have to place the argument? Where do you have to place the dummy return address? Understanding ROP would be a lot easier now that we have understood all this. Where were we? Such attacks are therefore known as return to libc attacks. Right. However, in principle, any available code, either from the program's text segment or from a library to which it links, can be used. Correct. So there the attack was to return to libc. But in principle, we can jump to any address we want, any useful function we want. So it doesn't have to be a function from libc. That is what they mean. We actually saw that before. We actually jumped to that new reachable func. Where is that? We actually jumped to this function. This was also, you can call it return to func, but the func is present in the executable itself. That is also possible. Sorry, I'm just getting used to this still. By carefully arranging values on the stack, an attacker can cause an arbitrary function to be invoked with arbitrary arguments. In fact, he can cause a series of functions to be invoked one after the other. See, that is very interesting. Here, we actually saw one, we actually executed one function, one libc function, that is system. We can actually chain a bunch of system instructions and bunch of libc functions, and that is also possible. I want you to try that out. Instead of giving a dummy return address, I want you to give a proper return address to which it will go and it will execute. Okay, so that was that. Why then did W XOR X see widespread deployment despite the existence of return into libc attacks? That's a fair question. The return into libc attack was came out in 1999 itself. But even after that, W XOR X was deployed at the hardware level. So why was that done? Perhaps the perception was that it would raise the bar for successful exploitation, or perhaps because only straight line return into libc exploits had been demonstrated. See, whatever it is, it will actually protect the system from certain exploit scenarios. It will definitely protect from executing machine code. It will definitely protect in such useful scenarios. I think that's why they deployed it. So because only straight line return into libc exploits had been demonstrated, or perhaps because it was thought possible to weaken the attacker by removing certain functions from libc. So along with W XOR X, if we remove access to system, or if we remove access from execve, if we remove access from such important but functions which can be used for malicious purposes, W XOR X can actually work. If I don't have access to system, then code injection is probably the only way, and I won't be able to do it because W XOR X is in place. So that is what they're talking about. As we show, this perception is false, but the thinking, whatever we understood is actually wrong. Return oriented programming generalizes return into libc to allow arbitrary Turing complete, it means any computation, without calling any functions. So they are claiming that they don't need any function to exploit the vulnerability. They don't need system, they don't need exec VE without calling any function. So this is pretty powerful. Even if you remove any function, ROP will still hold up and it will exploit. So there's something I wanted to tell here. Okay, so what I wanted to tell is that there is a function called mProtect. So set protection on a region of memory, right? So this can be used to change the security permissions of a particular mapping. So suppose we are executing code 1 here. We'll go back to this. Oops, sorry. So here we are looking at the memory permissions. So mProtect is a very powerful function. It can help you change this permission, change the permission itself. So that is something which is really interesting. So okay, so here code 1 is already has an executable stack because we set it to be to inject the machine code, the executable code. We will exec stack hyphen clear exec stack code 1. So now we'll run. Now this should not be there. The stack should be either write or it should be read and write. That's it. So now we are back to wherever we were. W XOR X is in place and this is there. But the function mProtect can help in changing the security permissions. So I as an attacker can come up with an exploit like this. Scratchpad. I as an attacker can come with something like this. Use return to Libc and call mProtect on stack comma executable. Make the stack executable first, then use normal shell code injection. Can we do that? In theory, it definitely works. It will actually work. So I want you to try this out. It's called a two-stage exploit. First, you use return to Libc and change the stack permissions. Second, you inject the shellcode in a traditional manner. So this is pretty powerful and it actually works. So that is what I wanted to tell. So if mProtect is present in the library, then shellcode injection becomes really easy. So okay, what is not our contribution? We'll just run through this without spending much time. Since the publication of the original paper on return-oriented programming, many researchers have begun referring to all exploits that reuse existing program code, including traditional return into Libc attacks, as return-oriented programming. Okay, I think that is normal. Anyway, this makes some sense. These exploits all leverage control of stack to run existing code sequences of the attacker's choosing, usually chained together with the return instruction. But if return into Libc attacks and the like are return-oriented programming, then it is no longer correct to say that we introduce return-oriented programming. I think there's a word missing here. But if return-oriented attacks and dash like are return-oriented programming, I think other code reuse attacks, I guess, then it is no longer correct to say that we introduced. Okay, so this lists a lot of other old attacks, so we'll just run through it. Clearly, exploitation that leverages control of the stack to execute existing code rather than injecting new code dates back to 1997 at least, with Solar Designer's work. I think that was return to Libc. Chaining several Libc function calls together was demonstrated for Spark by McDonald in 1999 and by Newsham and then Nergal for the x86. Newsham and later Dark Spirit pioneered the use of short instruction sequences in addition to Libc functions. Kramer in 2005 was the first to use short instruction sequences exclusively. So the short instruction sequences have been used before. Even showed how to use such ideas to combine unconditional loops. As McDonald showed, these techniques are usually sufficient to exploit WXRX platforms. A first stage written into Libc style loads and runs new machine code in an executable segment by means of a call to mprotect or mprotect on Unix and virtual protect on Windows. So this is good. I mean, this actually works. This will work. You need to try that out. Mprotect is a very powerful function. On platforms that allow the protection associated with memory regions to be changed in this way, McDonald's technique is a natural choice for the attacker. The technique is using mprotect and then shellcode injection. Turing completeness in the return-oriented stage is not necessary. You don't have to be able to compute anything and everything in the first stage. All the first stage needs to do is call mprotect, and that's it. Nothing else. The machine code run in the second stage is of course Turing complete. Our contribution is in showing that Turing completeness can be achieved without code injection. This has theoretical interest as an argument against defenses such as WXRX, but it has practical interest only on those platforms which memory protections are immutable, such as SQA AVC Advantage Voting Machine. So I think in they are telling that in platforms where WXRX can never be removed, even with mprotect or in any way, this ROP will be really effective, which is will be effective on those platforms. On less esoteric platforms, Turing completeness without code injection is irrelevant as a practical matter. And if return-oriented programming, meaning code reuse, is employed in exploits for these platforms, it is Solar Designer, these people who should get credit and not we. So yeah, I mean, in the while they were telling what their contribution not was, they actually listed a lot of really interesting exploit techniques, couple of defense mechanisms on their way. Mitigations. I think we will skip the mitigation for now. We'll come back to the mitigations later once we read through ROP, understand what ROP is, and probably have a demo or two, right? Okay, so that was all the basics. So I hope I'll just summarize everything for you. So all we did is understand exploitation, vulnerabilities, in specific Stack Overflow, and shellcode injection. We took a very simple example to demonstrate it, the exit of 0 example, and then we looked at return to Libc. We saw that we can get a shell, and we looked why WXRX can be effective in certain circumstances. WXRX effectiveness and how it can be bypassed by return to Libc. We saw that too. So these set the platform or the basis for return-oriented programming. Yes, we also read a couple of things about return-oriented programming, like it uses some short instruction sequences, or SQV, or they named something called as a gadget, and they told they'll chain instructions together, those sequence together to get gadget. They actually described a couple of things, but don't worry, we don't have to understand it now. We'll slowly read through the paper, and there's a complete section which will help us understand all these three. Okay, so that was some prerequisites which we needed to understand ROP. So any questions, if anybody is listening? Any questions? Okay, that's great. I will continue and let's go ahead with the next stage. Okay, we'll just clear off a couple of windows here. Okay, the exploits work is done. We'll just come out of it. We will come out of this as well. So we are set to go. Okay. So let's get started. The x86 and the Spark architectures. So we'll just quickly run through these architectures. We won't be going through Spark because I don't even have a simulator to run Spark programs on, and so we'll just go through the x86 and ROP on x86 first, and we'll understand it. Okay, so we present implementations of return-oriented programming on two extremely different architectures, the Intel x86 and the Sun Spark architectures. The two architectures differ in ways that are fundamental to the particulars of return-oriented attack implementation. So they mean they're really different. One has variable length instructions that need not be aligned to memory, and the other requires fixed length aligned instructions. One has many diverse complex instructions, while the other has a concise set of simple instructions. One features very few general purpose registers, while the other has so many general purpose registers that it even uses them to store function return addresses and stack and frame pointers. So this paragraph compares the two architectures. We'll quickly go through each and every comparison. So starting here, one has variable length instructions that need not be aligned to memory. So here they're talking about x86. So what do they mean by variable length instructions? We'll just go back to our disassembly. You can witness it here. So push EBX is a 1 byte instruction. It takes 1 byte to encode this instruction. Sub ESP, 0x0x8, it takes 3 bytes. So, and this is a call to some function. It takes 5 bytes, and then add EBX, some immediate. It takes 6 bytes. So it's something like this. So we saw 1, 3, 5, 6. There are actually 8 bytes, 10 bytes, so on and so forth. So we can actually see that. Where can we see? Witness 8, 9 bytes. Okay, here you see 7 bytes. I hope you get the point. I think in in x86 architecture, in the 32-bit variant, the longest instruction can be 12 bytes. I think in the 64-bit, the x64 architecture, the longest instruction can be 15 bytes. So it can vary from 1 to 15. Here we'll just focus on the 32-bit, the x86 architecture. That was the first. But in Spark, so that need not be aligned in memory. So memory alignment is a concept you will see now and then when you're talking about processes memory. So we'll just take a small. Okay, we are done with this. So what they're trying to tell is, look at. I'm sorry for the really bad drawing, but we can work with this. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. This is the, say each one is a memory cell. Okay, so each one is a memory cell, and so this, suppose this is the instruction, this is the data, this is the code segment of a program. Assuming this is Intel x86, the code segment would look something like this, where we can go back to this. We can actually copy it down. We can go to the first instruction. So here first instruction will be 5-3. It takes only 1 byte, right? So later it will be 8-3 and then EC and then 0-8 and then goes on. So there is no rule as to where an instruction should start. It can start from wherever it wants. It started here and then the second instruction starts here and then the third starts here, because the 0th byte first and then second, third, fourth byte. So there is no rule. But when it comes to Spark, it's not like that. There is a exact rule to place the instructions. So assuming these are assuming the Spark has 64-bit instructions, assuming, I think it has a 32-bit, but I drew a wrong drawing, so we'll just try. Sorry. So this is one instruction, okay? If it's an 8-byte instruction, okay? And then it's an 8-byte instruction. Then the next instruction should be here. So because the instructions are of fixed size, they will automatically be aligned. So there is no way they cannot be aligned. If it's 8 bytes, the next instruction will be at the 9th byte, right? So that is what alignment means. They are placed at certain. There is a rule to place every instruction in memory. That is what they mean. But in x86, there is no rule. You can this can be an instruction. This can be an instruction. This can be an instruction. So that is what they mean. The other requires fixed length aligned instructions, right? One has many diverse complex instructions while the other has a concise set of simple instructions. One features okay. So x86 is in computer architecture there are two types of computers, basically processors, CISC and RISC. You might have heard about it. CISC stands for complex instruction set computer. RISC stands for reduced instruction set computer. So complex instruction set is basically you'll have an instruction which is doing one or two things. It's actually complex. It doesn't. We'll take an example again. So what does push EBX do? It'll actually, where is this done? Okay. We can actually go ahead and okay. So suppose this is the stack, right? And then RSP is pointing here, right? And then I need to push EBX. So the I need to push EBX. So what does that mean? Push EBX is basically you put the contents of EBS onto the stack. So the stack grows a little bit, grows a little bit, and then place EBX here. Okay, or contents of EBX rather. And move the instruction pointer. That's very important. Move the stack pointer. The stack pointer is no longer pointing here. It's pointing here. So it's a conglomeration of two operations. One, placing the contents. Second, moving the pointer. All that is done in one single instruction. So that's the idea of, that's a simple example of complex instruction set. A lot of instructions are like that. It will, it is an encoding of various primitive operations. So here it was an encoding of two primitive operations, loading something onto the stack and then incrementing moving the stack pointer. But there are many other, but an instruction can encode many primitive instructions too. So this is a complex one, but at the same time in Spark, if you take, while the other has a concise set of simple instructions. So instead of push EBP in Spark, we might have to do something like this. We'll have to do so increment stack pointer and then move stack pointer comma EBX. So I hope you get the point here. EBX, so this is Intel format. I mean, this is, I don't know if ink and move exist in Spark, but I hope you get the point. Some register. So first you increment, you move it. Here some, nothing is there. And then you move EBX into this location. The square brackets means location. So here in Spark, we might have to use both the instructions, two primitive instructions, but here there is one complex instruction to do the job. So that, I hope you understand that. Okay, that one features very few general purpose registers, while the other has so many general purpose registers that it even uses them to store function return addresses and stack and frame pointers. So I mean, you can guess which one has a lesser number of registers here. Intel, the x86 architecture offers 8 registers, 8 integer general purpose registers: AX, EVX, ECX, EDX, ESI, EDI, EBP and ESP. So these 6 are general purpose. You can use it for anything. But EBP and ESP are actually, they are classified under general purpose, but they are not general purpose. They are special purpose registers. And ESP always points to the top of the stack. Basically, whatever we saw here. This is actually ESP working. The ESP needs to be incremented. So it should be increment ESP, move ESP, comma, I mean brackets ESP, comma, EBX. So x86 has a really less number of general purpose registers, but Spark, they're telling that there are a lot of registers, including a register which can have the return address. So in x86, the return address was stored on the stack. That is how we could get hand on the return address. But on Spark, it's stored on the on a register. So that is the difference. So they're just differentiating it. So we present the relevant features of each architecture, both to highlight differences and to assist in the understanding of the mechanics of each exploit implementation. So there are two intentions here. One is to highlight their differences. Second is understanding what properties of an architecture can help ROP, can help build an ROP exploit. Let's start with x86. Intel's x86 or IA32 architecture is a descendant of the instruction set of the 16-bit 8086 processor that in its 8-bit bus variant, the 8088, powered the original IBM PC. So, I mean, I can go into a bit of history. It'll take maximum of a minute. So, I think Intel started with the first 4-bit processor was called Intel 4004. Oops, sorry. Intel 4004. Some history, just to make things a bit interesting, I hope. 4004. It was 4-bit, as the name suggests. And then I think a couple of processors came, and then they've told it's 8088, which is an 8-bit variant. Right? Basically the size of 8-bit variant. And then came the 16-bit 8086. This was, I think, a hero. A lot of improvements were done when 8086 was in the market. The processor architecture was changed. Though it's a 16-bit processor, the length of the address bus was actually 20 bits later, because they wanted to address more and more memory, and 16 bits was not helpful. 16 bits can address 2 power 16 bytes, which is 64 KIB, I think. 64 KIB, which is actually less. So they increased only the address bus to 20 bytes, address bus to 20 bits, so that 2 power 20 addresses could be addressed. 2 power 20 is 1 MB. So you can see it's 16 times larger than what there was. So that's something. Okay, so now we are in the Intel x86 architecture. It's a 32-bit extension of these old architectures. So Because of its long evolution, the x86 ISA differs from more recent and coherent designs, notably RISC processors such as Spark. See, the Spark is a RISC processor. Many of the x86's unusual features are convenient for return-oriented programming. As we show, however, they are not necessary. So they are trying to tell that there are many unusual, weird features in x86 that make it really helpful, easy for return-oriented programming to work, but it's not necessary. So let's see. For additional information about x86 architecture, see the Intel's manual online. Oh, there are about 10 books, each book of size 800 to 1000 pages, and it's huge. There are a lot of instructions in Intel and a lot of other things too. Okay, memory. The x86 native machine word is 32 bits. Data is stored in a little endian format. The x86 allows unaligned memory access. Operations are possible on memory and some registers in 16-bit and 8-bit chunks. For example, AX names the less significant half of the EAX, and AH and AL names the less and more significant significant bytes of AX. Okay, we'll take the example of EAX itself. So remove all this. Okay, so EAX is a 32-bit register. That's what we know, which can further be divided into 8-bit chunks. So this is I'll use text. EAX, right? This is the 32-bit variant, 32-bit, and the 16 bits, the lower 16 bits is called AX, which is 16, lower 16 bits, and that further can be accessed, divided into two parts. One is this, and one is this. Oops. What is this? Okay, there's actually no gap in there. I just couldn't do it. So AH, which is the higher 8 bits, and AL, which is the lower 8 bits. Right. So this is how it is. And even in 32-bit, AH, AL can be accessed. There are instructions to access only the 32-bit, only the 8-bit part of it, or the 8 to 15 bits. This 8 to 15. So we can write it here actually. 0 to 7, 8 to 15, 16 to 23. Sorry, 24 to 31. So totally 32 bits. So this can be accessed individually. This can be accessed individually. This as a whole can be accessed individually and full. You can't. There are no instructions to access this and this individually. So the word EAX actually came. So it all started with. It was called a register A in the beginning, standing for accumulator. Later, that was extended to be AX, which basically stands for A extended. Later, it became EAX, which also means extended AX. So yeah, in 64-bit it's called RAX. Don't worry about it. R stands for register itself. So yeah, this is how the name progressed. So I hope you get this. So there are 8 general purpose registers, and this is how you can access it. The x86 allows unaligned memory access. So that is what I was talking about. You can access any byte, any address. That is the idea. There is no restriction. So if it's aligned, okay, my bad. I think we just draw this. Nothing more. In Intel, if a byte is here, this is one address, and say this is 8 bytes, or say this 4 bytes. So in Intel, it can access this byte, second byte, third byte, fourth byte. There is no restriction. But there can be restriction where the memory access can be aligned, meaning memory can be accessed only here or here or here or here. So I hope you're getting this point. So just, sorry, try so that's the difference between aligned and non-aligned memory access. Okay, okay, instruction set. Now we are actually getting to a important part. The x86 is a complex instruction register memory machine. So it also offers registers and it can access memory too. It's that type of machine. Most instructions can access memory directly by means of the mod RM and SIB bytes discussed below. We'll talk about it. This is a contrast to RISC designs with dedicated load and store operations, load and store instructions. Okay, so what do they mean by that? So in x86 there is a instruction called inc, which increments the operand by 1. Simple. It is just an increment by 1. It's basically x plus plus and nothing else. So here the operand can be a register which can be EAX, EBX, etc. Or it can be a memory location too. It can be some PTR or something like that, mem, basically increment memory location. This is also possible, but in RISC it doesn't happen like that. Increment doesn't have access to memory locations. It can operate only on registers. So if you want to implement increment memory, it should do something like this. So move reg comma mem, basically you are doing reg equals mem, and then you increment reg, and then you load it back, store it back. And then you store it back. You load it into a register, increment the register, and then you store it back. Move mem comma reg. So I hope you see the difference between why this is a complex instruction set and why this is simple. It offers very simple, very basic instructions, and the instruction in itself is simple. It's kind of restricted, but Intel offers a very vast instruction set. So so this is what I mean. This is in contrast to RISC designs with dedicated load and store instructions. So okay, this is also not correct, I'm sorry. So first you load, okay, and store. So this is how it will happen. It doesn't have a move which can move data from mem to register, register to mem. So there is a load which can get data from mem to reg, and store which will store back from reg to mem. So you can see this reg is reg to mem. So that was that. Okay, a variety of addressing modes are supported for operands, the most complex of which allows the programmer to specify a register base, a register index with a scale multiplier of 1 to 4 bytes and an offset. So to understand this, this actually we are dealing with the Intel instructions. So we can have a instruction something like this. So you want to move something into EAX. What do we want to move? We want to move a word, which is word of RAX, which is the base, and then we'll take RBX as EBX as the base, and then ECX into an offset. Right? So that is register base, register index with a scale multiplier of multiplier of 1 to 4 bytes and an immediate offset. Okay, it's not even this. It's actually this. It's this. Plus offset. This is what they mean. So where do you think this type of instruction can be used? Can you see use case? Can you see some C code you write which can be directly translated into this type of instruction? Huh? Okay, is there anyone? So okay, so the access of a 2D array can be directly translated into this. So you can see that. So you have an int array of 10 of 100, for example. So the EBX can be address of A. Okay, and then ECX can be, say you want to access the fifth row, say fifth row. Okay. Okay, so ECX can be 0. Scale can be 5. Okay, scale can be 5. So that ECX into 5 is equal to, it will give, oh sorry, wait a second, I'm sorry. So you want, okay, this can be 5 and scale is 10, sorry. So it needs to, scale is 100. The column size. So you go through this, and then what do you want to access? That you can specify in the offset. Which byte exactly do you want to access? So a 2D array access can be directly translated into this, one single instruction, and that can be loaded into EAX. That is how I would say amazing Intel instruction set is. So I hope you understand this. If anyone's watching, please put a question. If you don't understand, I'm always happy to answer the question. Okay, that was about instruction set. Okay, so there are bunch of this. Not only this, they talk about different addressing modes. So this was one addressing mode. One more example is actually D word. I'm sorry. So AX of word of say EBX, or wait, AX word of EBX. Basically, it'll take the 2 bytes and then put it into AX. So there's one clarification I want to give. The paper actually tells that the word size, the native word size in Intel architecture is 4 bytes, which is actually true. But when you write assembly code, it is somehow word actually means 2 bytes and D word or double word means 4 bytes. So I don't know where this discrepancy or confusion came from, but that is how it is. So I hope you get the thing. So you can do anything like this. So byte of EBX or something. So EBX is a memory location here. You want to read 2 bytes at that memory location and load it into EAX. You want to read a byte at EBX and load it into AL. AL is 8 bytes. AX is 16 bytes. I mean 16 bits. Sorry. So I think with that we can move to the instruction encoding. Instructions are variable length and unaligned, ranging from 1 byte to as many as 12. With some exceptions, instruction encoding is orthogonalized. Optional prefix specifying how to repeat string instructions, a 1 or 2 byte opcode. An optional mod RM model register memory specifying the addressing mode, and an optional SIB scale index base. I think this is what they are talking about. Scale index base byte used in some addressing modes, and up to 2 immediates each up to 4 bytes, specifying displacement and immediate values. So what they are trying to tell is they're trying to reason out why an instruction can be 12 bytes in size. So we've seen 1 byte. So a 12 bytes can have what is called as a prefix and the mnemonic, and then the addressing mode, info about addressing mode, and then two immediates. Immediates are basically constants, nothing more. It's just one other name. So it can have 12 bytes. So it can vary from 1 to 12. So if we, okay, there's one more point we think we missed with some exceptions. Instruction encoding is orthogonalized. Okay, one moment. Instructions are variable length and unaligned. So I hope you get the point. We discussed this in a previous paragraph. So okay, we'll just read from here. If we are given a byte stream and a starting offset, we can unambiguously decode the instruction at that offset. That is very important. So in Spark, I think the job is actually easier because the instruction is always aligned, the access is always aligned. So you know that starting from here, the next 4 bytes is an instruction, is one single instruction. Next here is one single instruction. But the same in x86, I mean, it's not the same in x86. So one instruction can be this big, one instruction can be 2 bytes, other instruction can start from here and end here, it can be 4 bytes, and it can be like this. So whenever you give a starting point, say you give starting point as this, you need to be able to tell that the next instruction is 2 bytes long and this is the instruction. That is very important even in unaligned access. So in Intel x86 that is possible. If if we are given a byte stream and a starting offset, we can unambiguously decode the instruction at that offset. So that's what they mean. So this is the starting point and 1 byte is the offset. I need to tell without any doubt what instruction this is, and that is possible. We will take an example for this. It will be really interesting. Starting from different offsets, we will find different instructions, including instructions never intended by the programmer or the compiler's code issue module if we start in the middle of an intended instruction. So, I mean, this is like the crux, the the foundation of using ROP on Intel. So this is a very important line. So I'll read it again. Starting from different offsets, so it can be this, it can be this 2, it's a byte. So this is 1 byte, this is 1 byte, so it can be this 2, this can also be a valid offset. We will find different instructions, including instructions never intended by the programmer or the compiler's code issue module if we start in the middle of an intended instruction. So the code issue module has done something like this. Let's take an example. It will issue okay, we'll take this itself. The code issue module has issued code something like this. So it has issued 1 byte instruction first, then 3 bytes, then 5 bytes, then 6 bytes. This is what the code issue module has done. But what they're telling is, this is the disassembler has split it like this, but this is nothing but a series of bytes and nothing more. 53, I'll just copy it down. 83, in memory it is just this, a series of bytes and nothing else. The disassembler has, see, it knows it can unambiguously catch the instruction. That is why we have the structure, but in memory it is like this. So we know this. Okay, we'll just put instruction stoppers here so that we know. So this is how it is. So while executing, the processor obviously knows it will execute 53 and then execute this, it will execute this, it will jump. But what we can actually do is, why can't we stop here or stop here at BB and try to see what instruction BB represents? Yes, the truth is the compiler didn't intend BB0000 to be an instruction. But what if we do it? Will we get something useful is the question. So we will take the same example and then we'll try doing something. Okay. So okay, so if it's getting long, that's okay. I mean, I want to cover a considerable part of the paper and then put the catch up later on the next stream. But yeah, so anyway, I'll upload the video, so you don't have to worry about it. Just wanted to let you know. Okay, so here we will take this byte stream and try to disassemble it. Okay, so we'll use a framework called Capstone. You can make a note of this. If you are following me, you can actually install it in a click. So sudo pip3 install Capstone. So this is a very crazy Capstone. Oops. Capstone GitHub. Okay, so this is the one. So it's a very good disassembler engine. So Capstone engine. Capstone is a disassembly framework, blah blah blah, with a target of becoming the ultimate disassembly engine. So it will help in disassembling bytes given a byte stream. So you can do that. And once you have installed, we'll write a simple Python program to disassemble it. I don't know the syntax though, but we'll just take an example from here. They definitely would have examples. Docs. Examples with Python language, right? So okay, awesome. They have an example here. We just copy it down and we'll try out something with this. Oops. Okay. So so we do this, and then the code present here, they have put some code. We'll put our code instead, right? Copy and paste. Okay, so this is not in the right format, so we'll have to format it. Okay, 3 more to go. I think it was 5.3. Yeah. Okay, so with that we are good to go. This is the instruction sequence we have, and it's very simple code with starting address of 0x100. You start disassembling it. So we will try to disassemble this. It should be the same as what objdump has disassembled. Okay, so objdump is, we close that window, we are using that window. Okay, so it's push EBX sub ESP 0x08 and then sub ESP 8. Okay, so here there's a push RBX, so I think we had to specify that this is a 32-bit binary, 32-bit code. I think we can do that somehow. Yeah, okay, yeah. CS mode 32. I think this should help. There you go. So it's push EBX sub ESP 8, call 0x10, this one, and then add EBX, so and so. So what you need to understand is objdump is a different disassembler. It's a I think GNU's disassembler, but capstone is a different one. But both of them, when given the same array of bytes, have unambiguously disassembled into the same set of instructions. That is one point. Second point is disassembling in the middle of instructions. This is something interesting. So what we can do is we can remove this. So we are actually in the middle. We are here, EC08. This is the code module, the code issue module didn't intend EC08 to be an instruction, but we'll see what we get. It can be invalid, but it can also be valid. There is a possibility. So yeah, that is a valid instruction. I don't know what in does, but if it's emitting instruction, then it should be valid. Or ALCH. CH is basically ECH, ECX, the higher 8 bits, the 8 to 15 bits of ECX. So see, it gave a totally different disassembly because we put our hand in the middle and try to disassemble it. Okay, so we can keep doing this. We leave this. Okay. We can start here. Okay, so the thing is, I think EC is a 1 byte instruction, so that's why this was removed, and then the rest all are same. We have to do something more crazy. We'll remove this. This is an 8-bit. This is a 5 byte instruction, so we will convert it into a 4 byte and then run. Okay, wait a second. Okay, so we got something here. We got a different stream. I mean, the 4th instruction was different, and this is obviously gone. Sorry, we can. So I hope you get the point. Even if we put our hands in the middle and then try disassembling it, there is a good possibility that it's a valid instruction. Why is this? Why does it work that way? I think that's because there are too many instructions. Okay, they've given here. Indeed, the high density of the x86 instruction encoding means that a random byte stream can be interpreted as a series of valid instructions with a high probability. It can be invalid, but there is a high probability that it can be valid because of the high density of x86's instruction encodings. Okay, so that was actually fun writing a very simple small disassembler. Registers. The x86 has 8 general purpose integer registers: EAX, EBX, ECX, EDX, EBP, ESI, EDI, and ESP, the way we listed. Each of this is 32 bits, the native word size. Yes, so here they've mentioned that it's a native word size, but while writing assembly code, word actually means 2 bytes, and D word stands for 4 bytes. D is double word. So I think in any assembly language it's like that. NASM or GNU. We'll probably, I think we'll write assembly code too with during this paper, so you'll witness it. As noted above, certain portions of these registers can also be accessed as 16-bit or 8-bit registers. In earlier iterations of the instruction set, these registers were more specialized, but now they're mostly interchangeable. So earlier there were 4 registers. Each of them meant something: accumulator, base register, counter, and then data. So you can see why they named it that way. Accumulator, basically it will store the results of an operation or a return value of a function. It's you might have heard that even calculators have accumulators, basically storing results, and this register is used for such things. B is the base register. You can you could probably store the base of an array. Say, so C is counter. Okay, it can be an iterator, or it was C was meant to be an iterator. I mean, D is for data, probably a data element, probably the array of, so basically B of C. Basically B is the base of an array, B of C will give some data element, right? Probably you store it in D. That was probably how it was, but now they are all interchangeable. You can use ECX for iterator, EBX for also iterator, EAX for also iterator. Everything is interchangeable. I mean, most of them. The notable exceptions are ECX is the stack pointer, which instructions such as push and pop manipulate. So that was the diagram. Okay, it's the older diagram, but so EBX cannot be used as a general purpose register for looping and returning values, stuff like that. ESP will always and should point to the stack pointer, to the top of the stack, which instructions such as pop and push manipulate. Push, we saw how it manipulates. Pop is just the opposite. In push, you push an element. In pop, you pop an element. So, I hope you are familiar with the stack data structure. This is exactly that. When you pop, you're removing an element from the top, and then you're moving the stack pointer below. So basically, you're doing something like this. Suppose RSP is here. Sorry, stack pointer ESP. When you pop, some data is here. When you pop, the data is removed from the stack. You know the obvious meaning of pop, and then this is changed, and basically the top of the stack changes. This is the new top of the stack. That is what pop does. So that was push and pop. EBP is conventionally the frame pointer as reflected in instructions like enter and leave, and ESI and EDI are source and destination registers for certain string operations. So when Intel is a complex instruction set, so it also offers certain string operations too. So for those instructions to work, they will use ESI and EDI. So ESI as the source and EDI as the destination. Probably if you're copying one string to another, ESI will be the base of the string, and then EDI will be probably the base of the destination string. So okay, so we actually skipped. EBP is conventionally the frame pointer as reflected in instructions like enter and leave. So now we have hit a very important concept. We came across a word called frame. So frame, whenever a frame, okay, we will take an example. Oops, new. Okay. So the stack is something like this, and the ESP points here. Okay. ESP points here. So when a function is called, so ESP points here, and the main, well, let's go back to code 1, and the main calls func. Okay, main calls func. So what does it do? We know what it does. It will remove this. The ESP points here. It will put the return address. It will put the return address here. It will put the return address, and then it will put the return address, and then the stack can be used by the func. Now the top layer is belonging to the func. So what part of the stack does belong to func? That is the question. Question is, belongs to func. So stack is used not only to pop and not only for control flow or pushing return address, jumping back to and popping it, but also to store local variables. If func has three variables A, B and C of say 4 bytes long, A is probably stored here, B is stored here and C is stored here, and they're all pushed onto the stack. So the ESP is probably not here while the function is executing. It's probably here. ESP. Right. So what part of this stack belongs to func? You can obviously tell me. I mean, it's fairly simple. This part, this part belongs to func. Right? So to ensure that the EBP points to the base of this part of the stack, EBP, base pointer, the register name is that. So this portion belongs to func's stack portion. So it's func's stack portion. So a fancy name for portion is a frame. This is basically func's stack frame. This is func's stack frame. And to signify that, obviously ESP will point to the top. The top will always belong to the current function which is executing, and EBP, which is there to make sure it points to the bottom of the stack frame. So that was a stack frame. ESP top points to top, EBP, as the name suggests, base pointer, points to bottom. Right. So I hope that is clear. A stack frame basically has all these things. It can have local variables. It mostly has local variables. It also has it can have whatever the program or the function wants. You can store anything. You can push in redundant random values too. It's basically like a scratch pad, right? It is like a scratch pad. Scratch pad for the function. And once the function is over, ESP returns back. ESP returns back to this place. Because once the function is over, there is no point in keeping that stack frame. It doesn't make sense. So ESP is removed and ESP is back here. Sorry. We'll choose a different color. ESP is back here, which is the top of main's stack frame. So this is main stack frame. I didn't mention that because I didn't want to. Main's stack frame. Once that is done, return address is pushed, and then func stack frame is developed. It's created using ESP and EBP push pop operations. Once the function is done, we come back to main stack frame. So that is the idea. So is that clear? EBP is conventionally the frame pointer as reflected in instructions like enter and leave. We'll see what enter and leave does. We'll come to that as we read some Intel code later. In addition to general purpose registers, the x86 has an instruction pointer, EIP, and EFLAG pseudo register used in conditional branches. Okay, so what they mean is not only that, but there are other registers too. We can use GDB and run. We can see what registers that does a 32-bit have. 32-bit architecture. So we saw EAX, EBX, blah blah blah. We saw EBP. We saw ESP. You can actually see this. See, ESP is 0x FFFF CA00, which is the top of the frame. So it has the pointer. It points to it. And then EBP 0x FFFF CA08, which is this, which is the bottom of main. So which signifies the bottom. It's main's. Currently it's the main's stack pointer, base pointer. So we were here. So apart from these, there are two other important registers, which are EIP, which is the which has the address of the next instruction to be executed.
See, the next instruction to be executed is this. The arrow points it will be executed next. So 565555 C8, it is the exact same as this. So that is instruction pointer IP. And E flags. E flags is a pseudo register. I mean, it's a register which is helpful in certain instructions, which is updated when certain instructions are executed. What I mean by that is, suppose we have an instruction compare, something like this. Compare ECX, say it's a counter. Okay, we'll start with 0. Move ECX, comma 0, 0, 0. We'll compare this with 13. Probably the length of hello world. Is it 13? 5 plus 5, 10, 11, 12, 13. Okay. So, okay, we need to compare it with 12. Okay, we'll compare it with 13. If it's 13, will come out. So, compare it with 13. If it is true, jump if equals to. If it is true, I mean if they are equal, if ECX is 13, then come out of loop. We can do this. So you jump, if it's equal, you jump out. So the JE is dependent on the output of compare ECX comma 13, right? Where is compare signaling that ECX is 13? That is the important thing. So it's signaled in the E flags register. One of the bits is set when their difference is 0. So I think it's called the 0 flag. E flags is basically a bunch of bits. Each bit is a flag which can be either 0 or 1, unset or set. So 0 flag is set when diff is 0. So ECX is 0, ECX is 13, and we are comparing it with 13. So there the diff is 0. So if it is equal, this bit is set. This bit is set to 1. Set to 1. Jump will look at this bit, the 0 flag. Oh, okay. So it is set to 1. So I need to come out of the loop. So I come out of the loop here. Come out of the loop is one more symbol which is used. If it doesn't come out, we can actually say print the character and then increment ECX. We keep doing this, and then we need to jump back to. Okay, so we have an opportunity to see one more instruction. Jump to loop, right? So you increment and then you jump back and then you compare. As you're incrementing, there will be one point where it is equal to 13. When it's 13, you come out. So the key here is the flags. There is a 0 flag. There are a lot of flags. There is a debug flag which will tell if a program is being debugged, like this. Right now, the debug flag is actually set, right? And there is a signed flag and so on. So that is E flags. Okay, wait, I'll just check if there are any questions. Okay, they're just my friends mocking me, probably. We'll just get back. I'm sorry. The calling convention. Okay, so I'm sorry. So I hope you get each and every function of a register and their names, how they came, some history, right? So in addition to the general purpose registers, the x86 has an instruction pointer. Oh, I'm sorry. I think I read this. E flag pseudo register used in conditional branches, and segment registers that support segmented access, mostly unused today in today's typical flat 32-bit memory access model. So here we have struck upon something interesting. Segment. What does a segment mean? So back then, when the memory model, currently the memory model is something like this. So a program is given addresses. If it's a 32-bit processor, a program's address, it's given an address starting from this to 0xFFFFFFF, basically 2 power 32 minus 1. So this is what is given to the program. Program can use all the addresses. This is because it's a 32-bit processor, there is a limit, but it can use any of these address. This is called a flat memory model because there is memory can be seen as a one single array of one single contiguous array of address memory. So of bytes. I'm sorry. Memory can be seen as a one single contiguous array of bytes starting from 0000 till FFFFFFF. So that back then this model was not followed. Something called as segmentation was followed. So I won't go in detail, but I'll just explain just to understand what these segment registers mean. I'll just give a small gist. So there were couple of registers. Okay, what all does a program have? So let us just list what all does a program have. It has a text segment or code. It has a data segment, basically all the global variables, and it has a stack, runtime stack, which is necessary for local variables and control flow, returning, popping, pushing, and all that. So it has a stack. So we needed. So back then there were registers which pointed to these segments. There was a code segment, basically code segment register, reg CS, which pointed to the code, reg SS, which pointed to the stack, reg DS, I think, which points to the data, and I think there was one more ES, which was extra. Right. So okay, now here I mean CS points to the beginning of the code, the first ever instruction, not even the first ever instruction, beginning of the code in the address space. So if we consider this, okay, this is helpful. Get PID, we'll have to go to the mmap file once again, maps. Okay, so here, if this was segmentation, just assuming this is the code, right? So if this was segmentation, CS would have the register 0x, what is that? The beginning address here. Just copy it down. This. So DS would be equal to this. SS would be equal to this if it was segmentation. And that way, because we know the offset, because we know the starting address, the rest of the things could be accessed. But this type of memory modeling, segmented memory modeling, went out of use, I think, when 32-bit Intel processors came out. These registers are still there. They're still there in current architectures. I think, can we see them? Okay, we'll just say info reg. Okay, great. So here you can see them. They have some values. They are still used, but not for not for this purpose, but for special purposes. We'll come to that. So there is a CS, there is a stack SS, there is DS, there's ES. Okay, later when the 64-bit processors came, they added two more registers. They're F and G. F and G have no meaning. After E comes F and G, so that's FS and GS. But they're still being used for special purposes. We will, I don't know if we'll see it in the paper, but we'll probably discuss it sometime later, right? So that was about segment registers that support segmented memory access, mostly unused today. Okay. Okay. So segments were used by some systems to implement W XOR X before NX XD hardware support was added. So you can see it's actually quite simple. The memory, the part of the memory pointed by CS should be only read and execute. Stack should be the part of memory pointed by SS is read and write. DS, so it's also data. So that was something. So I hope you get you have some understanding about the registers offered by the x86 architecture. The calling convention. Now we are actually going into a very important part. It is important for to understand this. Without this, we may not be able to understand ROP properly. Okay, so let's get to it. We'll actually spend some time on it, quality time. The calling convention. In the commonly used System V x86 ABI, the Santa Cruz operation. Okay, so the ABI stands for Application Programming Interface. Application Binary Interface. I'm sorry, ABI. So ABI is a set of rules which needs to be followed by every executable out there or every binary out there. What does this mean? I'll tell you. So we'll just read through. You'll understand what rules are. Function arguments and return address are passed onto the stack. So function arguments and return address push to stack. Why should we do this? Who told us to push arguments and return address to push on the stack? So what is this rule that we are following? This rule is followed everywhere by every binary out there. Binary, I mean, it can be an executable, it can be a shared object like Libc or the dynamic linker or any other library out there or any other program. Every function, every binary follows this particular rule. Why are such rules required? Why do you think they are required? So one obvious reason is consistency. Let's take a simple example and see how this helps. So I'll write a program. I have a compiler which will put arg1 into EAX, put arg2 into EBX, etc., and ECX, EDX, etc. till ESI, for example, EDI, ESI. So this is the way I am, and I push, I put return address. Okay, say I put return address in ESI. So let it be this way. This is the rule I am following for my program. My linker, my compiler will generate code like this. Now I call printf of Libc, which follows the System V x86 ABI. What do you expect to happen? What do you think will happen? So the program will crash. Nothing much. Mostly will crash because here my program has followed some rule and put arguments in these registers, but whereas Libc, which is following some other rule provided by the System V x86 ABI, it will push everything onto stack. It is expecting stuff on the stack. There will be something on the stack. There will be something on the stack, probably garbage. It will be used and then it will probably crash. That's it. So to maintain consistency, this application binary interface is made. See, look at this binary interface. That is what we were actually talking about. My binary interacts with your binary. What are the rules to be followed so that there is a consistent interaction? So these are a set of rules which are followed. So the rules are given by the System V x86 ABI. I hope you understand why it's called binary interface. There are various binaries interacting with each other because this is really important. I write a program. Some author the part of GNU writes Libc and some other library. Some other third party writes some other library, say lib third party, and I want to use it. My program wants to use some function which is part of lib third party. If lib third party is using its own set of rules, if I am using my own set of rules, there is no way they can interact with each other. Interact as in I can access and call lib third party's functions. That is not possible. So that's why there is a standard interface, binary interface here. So I hope you understand this. Okay, let's just check for any questions. Okay, they're still my friends. I'm sorry. So one of the main rules, I mean, will be x86 ABI is a very big document. It's a very big document. We can actually take a look here. x86 ABI PDF. Sorry, API. Sorry, ABI PDF. System V application binary interface. This is what we want. So this is a 141 page document which simply tells how binary which simply rules puts down rules so that binaries can interact with each other consistently. So this is an amazing document. If you have time, please go. I'll put this in the. Make sure you get this link. So it has a lot of stuff. It's amazing. So one of the main rules is function arguments. So because we day in day out we write functions and call them. So the rule which we'll focus on is function arguments and so and so. So function arguments and return address are passed on the stack. That is a rule given by System V x86 ABI. So I push the arguments onto the stack and call printf. Printf will fetch arguments from the stack. Okay, so that is how it will work. The call instruction pushes the caller return address onto the stack and transfers control to the callee. Correct. The return instruction pops a return address off the stack and transfers return to the address, to that address. So we will go back to this. We'll close a couple of things. I have 4 GB of RAM. I don't want it to run out of RAM because I'm even recording it. So okay, so we were talking about call and pop operations. We will draw the stack again. Here we point to ESP. Sorry, ESP points here. ESP. Oops. I think it's getting lagged or something. Okay, ESP it came. So this is ESP. And we witness a call. So there is a call to printf. Oh yeah, no, we'll actually take code1's example. We actually have written a simple function, right? So we'll just take code1, 1.c, 1.c. Shit. We'll actually simplify this. We'll write one more function which doesn't have anything except just the call and return. So void simple func has nothing in it. Okay, let us probably return a 0, which will help us. Okay, it has nothing in it, and we'll call this. So the program is modified. These are not useful as of now. So simple func is called, and then that's how it will happen. So we'll compile, we'll call. Nothing happened, obviously. The function has nothing in it. Idea was to use GDB and simple func be main run. So let us see how main calls this function. Okay, so here we are. Here there is a call to some address, some number which we see. So call some number. Oops. Okay, that was already in the copy. We will see what. I mean, you can see that the debugger is intelligent. It is telling that it is with the symbols. It's telling that we'll be calling simple func. We'll ensure that we'll disassemble at this address. You know, this as is the argument. I mean command, GDB command. So it's fairly simple. You disassembled, this function will happen and then come back. So we will call it. We have not yet called it. We'll call it. So look at the stack. So once you call it, this is the return address. After simple func is executed, oops, this is the return address. So we will go ahead and execute call. So this was the old one. So here is our return address, and there is one more. Something has been pushed into the stack. So we'll look at what that is. So push EBP. So the base pointer of main, we'll see, mains base PTR is pushed. Why exactly? Why do we need to push the caller's base pointer? You need to push it because now, because we are in func, simple func, EBP should point to this function's base, not main's base. So EBP would be changed. EBP will change and point to func's base, stack frame base, right? So because we are changing EBP, we need to store it somewhere. If not, we will be losing the pointer to the mains stack frame. So we push it onto the stack. So here we are using stack for something more. No, it's not a local variable. It's not a return address. It's something we want to store now, so that will be useful later. We need to, once func is done, see here you can see a pop EBP. Once func is over, the old EBP, mains EBP is pushed, is loaded back to EBP and then only returned. So that is how it happens. So we are, okay, so don't really worry what this call is going to. It's as of now it's a bit complex to explain. These two, we'll come back to that at some time. So as of now, focus on these two, where you push the frame pointer. Oops, sorry. You push the frame pointer. One sec. You push the caller's frame pointer and then you update EBP with ESP. Why ESP? We know that ESP should point to simple func's base, stack frame base. Why is it ESP though? We can take a look at this. So here we are ESP. So first you push in return address. First you push return address. And then you and then we are now ESP is not here but here. Oops, I'll take the thicker one brush. Here. Now ESP is here. Now what we are doing is we are pushing EBP, right? We pushed EBP, basically mains EBP, or more in general callers EBP, right? So now ESP is not here. We'll just copy this. It's here. It's the new position. It's here. Now we are executing an instruction called move EBP comma ESP. Basically, the EBP register will also point to this now. After we'll just move EBP comma ESP, which implies EBP equals ESP after it's executed, right? So after it's executed, it will also point to this EBP. Now we have a stack frame. EBP is pointing to something. ESP is also pointing to the top. We have a zero sized stack frame. So this is now we start with 0, right? Now we have a stack frame ready. Though it's zero sized, we have a stack frame ready. If we push something, ESP will move up, EBP will remain there. It will keep quiet and remain there. So everything happens, and then pop EBP RET. Okay, so we will actually modify this function a little bit. It's simple, but it's too simple. Int A, int B, int C. We will load say 10, 20 and 30. Okay, so now we have not so simple simplyfunc. Oops, I need to compile it. Even now it won't show any output, but the internal stack memory would be different. We'll break at simplefunc. You know how call works, so we'll skip that. We'll just right ahead go to simplefunc run. Okay, so here look at this. So push EBP is done, move EBP ESP is done. So both are pointing to the same, to the top. We have a zero size stack frame, and then there is a sub ESP 0x10. So there might be a bit of confusion here. I'll clarify that, don't worry. So the ESP is pointing to somewhere here now. EBP remains there, EBP is still there. ESP remains, EBP comes here. ESP, the stack pointer comes here. When I am subtracting a register, why is it moving up? Right? I mean, I'm subtracting 0x10, basically 16 from ESP, but here in the diagram, I'm showing that it's moving up. So this is where Intel's architecture comes in. A bit of explanation is needed here. In the memory layout, stack always grows downwards, basically. Okay. File new. Okay, same. In reality, if you consider the complete memory space, like the maps file basically, so the text starts somewhere here below, text somewhere here, probably later data. Okay, there was a read only here, it's okay. Text data. Later comes the heap. It's heap, from which memory is allocated dynamically, right? You know the heap. Malloc and calloc get memory from the heap, right? So these are three. Now there is more in this address space. There are shared libraries too, right? So where do they come? So they have been placed somewhere in the middle. Okay, that's too close. So the text is here, data is here, heap. It's dynamic. It's called dynamic. If we allocate all of this space, it'll move up See, look at this. See, this is, we are starting at this point is 0x00, 0x00000000, right? This tip, text is somewhere there, data, heap. Heap starts at this point, and then once all the heap memory as of now which is allocated is over, which is allocated to the process, it will move up. It will allocate more memory. So the addresses in the heap will become bigger and bigger. This is the shared library. So you can think about this as the base, basically base from where all the libraries will be stacked upon. So probably Libc is here. It's mostly the first library which is loaded, Libc, and then say one more lib third party, libabc, and one more libbcd, something like this. So shared libraries come this way. But what about the stack? Where is the stack present? Stack is present up above here. Stack goes here. STACK, okay, stack. So ESP in the program is probably somewhere here, is probably pointing somewhere here, right? ESP is pointing somewhere here. So when we want more memory in the stack, ESP is incremented, not ESP is decremented. It goes below. See, this is lower side of address. This is the higher side of addresses. If we need more memory in stack, we need to decrement it. So ESP here, it goes here, probably goes here. And this amount of memory is given to that function which is calling this. So in the same way, where is this? In the same way, sub ESP 0x10 will subtract 0x10 and allocate 16 bytes of space, right? And then, okay, we'll ignore this. And then we are storing some data there. Data, store A. This is A, 0x A, which is 10, variable A, variable B, variable C in the stack. And then once everything is done, we put, we are loading 0x0 into EAX, which is basically the return 0. So this is, we have encountered one more rule alert. So return value loaded into EAX, right? Though this is one more rule. Okay, once everything is done, here when I'm trying to load the return value, it means I'm done with the function. I need to leave right now. So leave is one more function. Oh, okay. What does leave do? And then RET as well. So we'll go back to the image and then figure it out. Okay, there were unsaved image 2. So where is the unsaved image 1? Okay, it's not shown here. We'll just close it. Now here. So this, you understood this, right? We'll say it's decremented, but it's allocating more memory here. It's allocating more memory. So once everything is done, what do we need to do? We have the following job to do, right? Looking at this diagram, we can actually figure it out. Once everything is done, deallocate memory. Correct? Obviously, we can't. Once the function is done, we need to give away that memory. It's not ours anymore. Deallocate that memory. Load EBP back, because we are returning back to main. And when we are in main, EBP should have main's value, right? Load old EBP back to EBP register. So this is very important. And then return. Right. So here we allocated 16 bytes using sub ESP comma 0x10. How can we deallocate it? It's very simple. Add ESP 0x10. You just simply move the ESP back to its original state. When it was the original state, meaning the state of ESP when the program was just called, it was equal to EBP, right? That was the state. So when you do that, ESP and EBP are same. So this will help. Later, then we need to store back mains EBP onto EBP. So let us pop it off. Sorry. 1, remove this. 2, pop EBP. Because when when add ESP comma 0x10 is done, ESP is not this anymore. It's actually pointing to this. ESP is here. So when you pop it, ESP, I'll start writing on the right side. So this was during the function call. This is when we are cleaning up. Clean up. I need to get better at representing all this. I'll do that probably in the next stream. Yeah. Clean up. So now ESP and EBP are the same here. ESP comma EBP both, right? Now we'll pop into EBP. What will that do? That will take this mains EBP, which is top of the stack, and then push it. Load it into EBP. So that has two. So ESP will now, after executing pop EBP, will now point here, and EBP has its original mains value, right? So now ESP is here. Now we are ready to return. Memory is reallocated. The EBP points to the caller's, base pointer, basically stack frame. Now we are set. Let us just return. Nothing more. So return obviously uses this address given here, the top of the stack, and then returns. We have seen that in the functions. So coming back to what we were talking about here. The call instruction pushes the caller return address onto the stack, correct, and transfers control to the callee, correct. The RET instruction pops a return address off the stack and transfers control to that address. So I think they have specifically not told that the RET instruction pops a return address off the stack and transfers control to the caller. So they have not told that. They have simply specified to that address present here. And I think we can reason out why. Because there are ways to overwrite this return address. So whatever address is present at that moment before RET is executed, control will be transferred to that address. Not the call. May not be the callee. So that is the idea. Then they've told the x86 stack grows from high to low memory. So that was the previous image. So I hope it's clear. Arguments can be pushed in any order, and different conventions specify either first argument last on stack, C style, or the opposite, Pascal style. So when you're using C style, all libraries should follow the same rule. When you're writing code in Pascal and compile using Pascal compiler, then it can be different, because you'll be using the corresponding Pascal libraries which will be following Pascal's type of ABI, right? So a function's return value is put in EAX if it is 4 bytes long. A function's return value is put in EAX if it is 4 bytes long, or in a combination of registers if it is longer, right? So we also saw that too. We had a return 0 in simple func. Where is that? Yeah, it's here. We had a return 0, so that's being reflected as a move EAX, 0x00. If it is bigger, probably if I want to return an 8-byte register, 8-byte value, then probably the first 4 bytes will go into EAX, and probably the next 4 bytes will go into EDX or any other register. I am not sure about it. Reading this ABI would give more details. Okay, of the general purpose registers, EBX, EBP, ESI, EDI are conventionally callee saved. EAX, ECX, EDX, ECX and EDX are caller saved. Okay, so here so what this means is, so when a function call happens, I hope this part is clear. The formation of stack frame part from 0 to bigger stack frame and then going back to it. So of the general purpose registers, EBX, EBP, ESI and EDI are conventionally callee saved. So going back to this diagram, you can see that once function was executed, okay, we can actually go, once we are inside the callee, which is the simple func, it stores EBP, right? It actually stores EBP. So similar to this, the ABI tells that EBX, ESI and EDI are also callee saved. So it should ideally save these registers. So I think here it's not being saved because it's not being used here. If the body of the function uses ESI, EDI and EBX, I'm pretty sure it would be saved like push EBX. There will be a push ECI, push EBX, push EDI, push ESI, and later the body, those registers can be used here. So because it's not being used, I think they're not being pushed. So that is the argument. Their callee is saved. So the callee saves it on the stack, in its stack frame. And EAX, ECX, EDX are caller saved. It is caller's responsibilities to store EAX, ECX and EDX, right? So 4 registers are callee saved, callee responsible. 3 registers are caller responsible. So this is the rule given. When EBP is used as a frame pointer, the idiomatic function prolog is the beginning, reads push EBP, move ESP, EBP. Okay, so here I want to point out something. So the syntax, the assembly syntax that I've used is called the AT&T syntax. So this is the default syntax which GNU assembler uses too. So it's actually a bit different from the syntax we have seen so far. So I'll just write it down here. Push EBP is fine. Okay, move ESP, move %ESP, %EBP. But what we saw here is move EBP, ESP. It's just the reverse. So it's basically syntax and nothing else. So what we used was Intel syntax. So it's opcode or mnemonic destination, source. AT&T syntax, mnemonic source, destination. I hope now it's clear. So even here it's ESP's value is getting copied to EBP, just that the way we write is different, the syntax is different. So you will, if you explore these two syntaxes, you will understand that AT&T syntax is a bit cluttery. I mean, it has stuff which is unwanted, things like percentage. I mean, percentage signifies that it is a register, I agree, but it's not needed. So we'll mostly be dealing with Intel syntax like this. But yeah, paper uses AT&T, so we need to be careful while interpreting whatever they've given. We need to read it through AT&T syntax's eyes, right? So coming back, idiomatic function prolog reads push EBP, correct, move ESP, EBP, which is basically move EBP, ESP, because they are equating both of them, nothing else. The idiomatic function epilogue, which is the ending, reads move EBP, ESP, pop EBP. So basically in the end, what did we do? We did add ESP comma 10, but they are doing move EBP SP comma EBP. What is the difference? Even here we are cleaning it, right? We actually cleaned it. We increased the stack pointer so that the 16 bytes could be deallocated. That's clean. That's cleaning. That works. But even here, it actually works. So let us see why. We'll go back to the diagram. Okay, we are here. Okay, we go back to the function calling part. So ESP is here. Please, okay, I'll be using red. It's actually easy to check. ESP is here. Okay, EBP is here as usual. Once everything is done, ESP should be reduced to EBP. That is the idea. So instead of doing add 0x10, which is the size of this, we simply equate ESP to EBP. So what we do is ESP to EBP. Why is it helpful? Why is it better? Because when we do add ESP comma 0x10, what we are doing is we need to know how the size of the stack frame, right? We need to know this size. But when we do move ESP comma EBP, shit, I made a mistake. It should be ESP comma ESP equals EBP. When we equate it, we don't need to know the size of the stack frame. Automatically, irrespective of the size of the stack frame, ESP is set to EBP and the stack frame size is reduced to 0. So yeah, that is the convention. So coming to the leave instruction. What does this do? This is an alias for move ESP comma EBP, the cleanup, and pop EBP. Nothing else. See, you don't see these two, but we need to do these two. So leave basically later is decoded into these two instructions. So that is leave. Enter is basically these two. They've actually mentioned enter in the paper, enter and leave somewhere, I think in the instructions, or sorry, I just missed it. Okay, so sorry, here it's like enter and leave. So this is leave. Leave is nothing but an alias for these two. Enter is nothing but an alias for the opposite of this. Basically push EBP and move EBP, move ESP into EBP. So that is enter, this is leave, right? So where were we? We are in the calling convention. Okay, arguments can be pushed. Okay, so we caller save, right? When percentage EBP is used as a frame pointer, the idiomatic prologue, we know the prologue and the epilogue, basically the starting and the ending. The x86 includes instructions to support ABIs that differ from the one described here. While these instructions generally do not occur in a program, do not occur in normal programs, they can sometimes be found in the unintentional instruction streams found by jumping into the middle of intended instructions. We saw this intended and we saw this jumping into the middle of the instructions example. So we wrote that small disassembly program using Capstone. So most importantly, for our purposes, the x86 ISA actually includes 4 opcodes that perform a return operation. So what is this all about? It's return oriented programming. So it's all about returns, all about the return instruction. So there are 4 types. That's what they're telling. Opcodes that perform a return instruction. C3, near return, the version used in the System V ABI. So C3, we can find it in our programs because all the programs, the binaries which are generated follow the System V ABI. So where were we? Near return. C2 immediate 16, basically a constant of the size 16 bytes, 16 bits. Near return with a stack unwind. CB far return and CA immediate 16 far return with stack unwind. We'll come to that. We'll understand what they are. The variants with stack unwind having popped the register return address of the stack increment the stack pointer by immediate 16 bytes. This is useful in calling conventions where arguments are callee cleaned. So this is something we need to discuss. So we told that the System V ABI pushes when requires the binary to push arguments onto the stack. So before the function, we obviously need to push the function, push the arguments before the function is called, right? So we probably push it here. Say this is arg1. This is r2. Right. We push and then go back, call, etc. So while returning, the callee has two choices to make. One, it can just return and then leave cleaning up these arguments to the caller. The caller needs to clean up these, remove, deallocate this stack by moving ESP from pointing here to somewhere here. Basically deallocate memory. Or it can clean the arguments itself. That is what they mean by callee cleaned. Here, where is it? The variants with stack unwind. Stack unwind is just a fancy name to tell that the RSP is ESP is moving backward. It's unwinding. Having popped the return address of the stack, increment the stack pointer by immediate 16 bytes. See, it was ESP was here. You can probably increment it till here and clean this up. I mean, it doesn't work that way because return address is here, but something like that. Basically, the callee is responsible for that. So this is useful in calling conventions where arguments are callee cleaned. So that's about it. The far variants pop %CS off the stack as well as EIP. Okay. All four variants can be used in return-oriented programming, though using the three besides C3 is more difficult. For the far variants, the correct code segment must be placed on the stack. For the stack unwind variants, a stack underflow must be avoided. So that was the problem I encountered now. So the stack frame is still here, but if I shouldn't try to decrement ESP from here to here, because the stack frame is only till here. So that's stack underflow in simple words. So what they're telling is we'll mostly be using C3 variant. C3 mostly used. So that, okay, wait, we can actually come out. We'll go to the, okay, there's one more. Okay, there's one more terminal here, right? So we are in the beginning. So we have phi 3, 83EC08, E8 so and so, 81. There is a C3 here. See, actually these 6 bytes mean add EBX, 0x1BEB, some constant. But if we take just these two instructions, these two bytes and try to disassemble it, let us see what we get. Okay, we'll simply use RASM to disassemble it, the radar module. Oops. So I think we got an invalid. So that was invalid. Bad luck. I just want to try this. So this is it. We'll just run this. Hey. Okay, so it didn't print anything because I think there was an invalid instruction. Probably that's why. So Okay, so probably if we put 5 here, I'm just assuming, say we put 5 6. Okay, so it's a valid instruction. So I mean the idea is that, let us go back to the code. Okay, it was here. The idea is that C3, the instruction C3 EBIB. Okay, we will check this out just one more time. We will see if we can get something meaningful in the middle. That is the idea. Oops. So that is the code. Let's run. Okay, so that is something meaningful. So basically, we did not. It was not. This instruction was not intended to be present. Okay. So if we jump here and then disassemble these three, we actually get a different instruction. We get an RET followed by I think it was a move ESI something. So idea is you can jump in the middle and then get meaningful instructions. We actually saw this. So that is about the calling convention. That was about x86, a short intro. It has 8 registers. Let me just sum it up. It has 8 registers, lots and lots of instructions, variable length instructions, memory access is unaligned. You can access any byte, unlike Spark. There is a convention called System V ABI, which we are all following, which our binaries will follow. There are other rules too, but I think we most of the binaries here follow System V ABI. So I think that's about it. And the return is encoded as C3. I mean, there are other 3 variants, but we'll probably be using C3. So that was, and I hope you have understood, the way function call works, the way return address, the way ESP is manipulated, to increase the stack frame size, etc. So this was a small intro. So I know it's taking long, but I don't want to skip all this and then go to ROP, because in understanding ROP directly without understanding all this will be really hard. I found it impossible without knowing all this. So it's long, but I'm sure it'll help. So before moving to the next part, we'll take a small break, and okay, before that we'll see if there are any questions. Okay, there are no questions. Okay, we'll take a small break here. We'll come back in 5 minutes. Whoa. Okay, we are ready to go again. So let's, will get reflected. Alright. Why is it not getting reflected here? Okay, great. There is a bit of delay. Okay, so so far we have covered some prerequisites. Everything here is a prerequisite. Say, be it the attack defenses, W XOR X, the shellcode injection, and the W XOR X stopping it, and then return to Libc, breaking it. Each and every thing we did, and talking about x86 architecture for a while, and understanding the rules, the System V x86 ABI were all prerequisites. So let's start. But the next section, 3.1.6, right? Buffer overflows on the x86. Right. Now I know every time we enter a new section, it is actually an interesting section. There is something new and awesome. So, okay. We have already discussed buffer overflow techniques generally in section 2. Because of its dominant position as the processor because of its dominant position as a processor in general purpose desktop computers, the x86 has received substantial attention as the target of low level attacks such as buffer overflows. So the number of processors out there in the wild are more. So there is more attention to it. Because if you attack Intel, if you find a vulnerability on an Intel machine, you probably can attack too many of them, because Intel machines are everywhere. So that is what they mean. Its particularly useful architectural features from an attacker's perspective are the placement of activation record metadata, such as the saved return address on the stack, where it can be overwritten by a buffer overflow. We saw that the return address can be overwritten by a buffer overflow. There was a buffer, we used a stupid function, getS, and we were able to overwrite the return address. But here they've used three words, activation record metadata. So activation record is the generic term for stack frame. So we use stack frame, activation record. Just think about it. Where is that? Think about it. Why should the local variables be stored in the stack? What is the rule? Why should they be stored? They can be stored in the heap too. Right? They can be stored in the heap. But they're not being stored. They're stored in the stack. There are a few programming languages which store all these variables in the heap. So it's not called a heap frame. It's called an activation record. So the generic term is activation record. You will probably encounter this when you are learning programming languages. Generic term is activation record. I think it means a function being activated. Just that the activation record is placed in the stack in x86. It is placed in stack in x86. That was activation record. But activation record metadata is stuff like this. Say the return address and probably the EBP2. So those are activation record metadata. So I hope you understand what activation record is. It can be stored in stack or it can be stored in heap. There are languages which store activation records in heap too. But here in x86 it's stored here. And activation record metadata is one example is the return address, which can be overwritten by a buffer overflow, and we saw an example. And the unstructured calling convention and the use of frame pointer, which makes possible chained return into Libc attacks. So this is what we didn't explore, chained return into Libc attacks. So after calling system, exit could be called, right? If you remember, we can actually go back to the exploit. Okay, we'll open it up here. So what we did is system expects the return address. We actually gave some trash, which is trash. But we don't want it. If we give some trash value, there's a high probability that the program will crash, right? If we want it to end peacefully after our journey of exploitation is done, we can put the address of exit here, don't you think? So we can actually put it. We will get the address of. Okay, so we need to break somewhere. We need to be in the process state. Print exit. So exit is present at some address. Just print system to make sure it does not move. Right. So exit is here. We will put exit's value here instead of trash. We'll see what happens. Okay, wait. Before that, I want to run it with the trash value to make sure to show that it will crash. So cat payload ./code1. Oops. Okay, I think we have changed the shit. We should be calling func here. Compile. Okay. So we have the shell, we saw this. Then we do a control C, it check faults. Basically we come out of the shell, the /bin/sh, and it check faults. Instead of that, we can give it a peaceful termination. It's anyway terminating, let us give it a peaceful one. So instead of trash, we also saw that it's because of this trash value. So of this, we will give the exit value. So this should ideally exploit .py. Okay, that's it. See, look at that. It was so silent, so peaceful. It exited without segmentation fault. If you think about it that way, we don't even have to exit. We can go back to where to the actual original return address of main. We'll try doing that. So you saw a simple, very simple chained return to Libc attack where system was called, later exit was called, right? So we will actually go back to the actual original return address. It's just an experiment, nothing more. Okay, so this as main, this is the return address. Okay, so we put it here. We'll comment this out. It's important. It's a chain attack. So we'll see if this actually works. It might actually crash later because the memory is corrupted. It's not all clean, but we can actually try this out once. So basically, if we exploit.py, okay. So if we are able to see after func, then it means we have succeeded. Okay, that's the idea. Let's break at func. Let's run payload.txt. Okay, let's go. Okay. Okay, so here it will give okay, so the debugger is not helping us here because it will stop and so we will we'll put the payload directly. Oops, no, it didn't work. Let us check why. This is the address, right? Yeah, that is the address. So it needs to jump back after that. So exploit.py cat payload ls. This is what will work. No, it's exporting. So I think we need to debug. But once the new, okay, so how do we clear the breakpoints? Shit. Okay, I don't know if I'll just do the very brute way. We'll just exit. Let us not break anyway. We'll simply run payload.txt, right? Okay, the the debugger is not helping us here. Okay, I think we can try that out later. But see, that's a nice experiment. If you can make sure that the program carries on, runs properly later, once you are done with whatever you want. I mean, that is as silent and as stealth you can be, right? Stealth is silent and maliciously silent. So okay, let's go back to the paper. Okay, okay, we saw a very lame, like a very naive chain return into Libc attacks. Later we will see more. The x86 and the return-oriented programming. Several features of the x86 ISA make it an attractive platform for return-oriented programming. The instruction encoding is variable length and unaligned, giving unintended instructions if one jumps into the middle of instructions, middle of certain instructions. The instruction set is large and its encoding is dense, so a variety of instructions are available for use even in relatively small programs. Because if there's a 15-byte instruction, you might find 3 or 4 more smaller small size instructions in that 15-byte long instruction. That's what they're talking about. There are few general purpose registers, so it is often possible to coordinate data flow in a register between two useful instruction sequences. Okay, let me read it again. There are few general purpose registers, so it is often possible to coordinate data flow in a register between two useful instruction sequences. The calling convention uses the stack, correct, which an attacker can often overwrite, which we saw. If there is a stack overflow vulnerability, there is all the chances that we can overwrite it. And it is relatively unstructured, so the instruction sequences ending in RET can generally be chained together. I think they use unstructured as a combination of all this variable length, unaligned, unintended instructions, and the ABI being and because of the ABI. So okay, that was about that is the in this paragraph, what the author is trying to tell is how can return oriented programming benefit from x86's features, right? So variable length, unaligned, all of them are really helping an attacker to use ROP exploit, to use ROP as an exploit method. So with that we finish the x86 architecture. That was a very nice and small intro. And then now comes the Spark architecture, which I'll be skipping. We will look at the we'll look at ROP on x86 Intel architecture. Okay, so we have been on for 5 hours 7 minutes. That's a long time. So I think we will end it here. We can end here, and yeah, I mean the main crux of the paper is return oriented programming, and we still haven't started it. We just went through a couple of things like gadget, chained instruction sequence, RET, and jumping in the middle of instruction and stuff like that. We really didn't look at the principles of ROP or program layout and how it should be and stuff. So, but I hope that was I hope you could understand all of it. I hope that because all of that was intended to be a good prerequisite to understand ROP. I mean, that's the sole. That's also one of the reasons why it's put in the paper. All the attacks, all the defenses, the architecture. Understanding the architecture well will help in coming up with better exploits. So, I think with that we will. I'll conclude this stream. In the next stream, probably tomorrow or day after, we will take up we'll take up return-oriented programming and make sure we get a proper demo, working exploit, proof of concept. So this is how colorful it is. It's too good. So we'll go through it, and I hope you get the point of ROP. It's basically an exploit technique which can reuse code present in the program address space, basically libraries address space or the program's address space itself, without injecting any code. Okay, I hope now the abstract is making more sense to you. I request you to read the abstract again. Now I'm 100% sure it will make way more sense than what we try to understand in the beginning, because there are a lot of heavy words present there, CW XOR X and all that, but we have seen demo here how W XOR X works, how it will protect us from the attacker from running machine code, the injected code, and how ROP or return to Libc for that matter, return to Libc helps in bypassing that. So with that, I think I'll end. Just two more things. I want you to try these out. One, use mprotect to change stacks permissions, and then try code injection. Right? So you're basically defeating W XOR X. That is the first one. Second thing, I want you to implement the chained a more complex return to Libc attack. So I mean, it's not homework, but it's good exercise. You'll come to know if you have actually understood what we did in today's stream. So it's a really good exercise. So with that, I will end the stream. Oops. Okay. I hope you liked it. Please, if you watch it, I'll be uploading a copy of the record of this stream on YouTube. I am sure there would be a couple of mistakes which I've not noticed. I realized that I need to make my presentation better. I mean, this is okay, but not so okay, because it's too cluttery and someone who comes in the middle won't be able to understand this. So in the next post, when we try to read the fourth section, the ROP, the main section, I'll make sure my presentation is better. And I was too nervous in the beginning, but now I think I'm okay. Okay, thank you so much, whoever is still listening to me. Okay, I don't know anyone, but thank you so much for coming in. It was a really new experience for me, because I'd never done something like this before. I'd taken a few small sessions in my college, teaching simple stack overflow or understanding memory layout and stuff, but taking a long session like this, it has I always wanted to do this. So I hope you I felt really happy. I hope you learn something new, understand something. If something is not clear, you can comment it out here, or I'll be uploading the video on YouTube, so you can comment it out there too. So if there are any mistakes, technical, or if I can improve on something, so please, please mention it. Don't even bother. So please mention it. Don't hesitate, because it's important that I improve on things. I mean, that's one reason why I am doing this. Okay, I think with that, I'll end the stream. Thank you so much. Thank you.